afternoon.
Yeah, I'm excited for today. It seemed like had some new people coming in, some new faces. I'm excited for anybody who's been here before, and also anybody who's here for the first time. Yeah, the last couple of meetings, we've been, stepping our way through cubism. It's definitely something that I've been interested in over the last couple months. And, just to refresh your memory or just as an introduction, if this is your first time, I would say cubism has sort of like two components. One is a sort of mathematical reformulation of standard finite dimensional quantum theory in terms of probabilities. And the idea is you can sort of look at quantum theory as being like probability theory with a little extra. And on the other hand, there's a philosophical argument being had as well, which is that quantum states are not to be regarded as descriptions of physical systems, but as useful representations of like our beliefs about them. And then also, given that we have to extend probability theory in a certain way, there's kind of a deeper ontological or metaphysical question that the cubists are, I would say, only beginning to sort of understand or work through, which is, trying to come up with a statement like, what is the world like? What must the world be like, such that it's useful to gamble upon quantum systems in this particular way? And so that's, I would say one of the things that makes it distinctive. Today we won't be carrying on, like the full philosophical argument. My motivation was, the cubists have some great papers, some technical, some more expository, that give a really good introduction to the theory. But one thing I was thinking is that their concern in the papers is often to relate their particular reformulation to the standard formalism. So it sort of assumes you're already familiar with your complex vectors, your probability amplitudes, your Hermitian matrices, your unitaries, et cetera. And, they'll try to like derive, the probability-based formalism from that, and, and then carry on this more philosophical argument about it, and, in general about the nature of probabilities. But I thought, there's sort of, to my mind, a need for kind of like a more self-contained introduction where like you don't even mention any of the standard formalism. Like, what does it look like if you don't even mention the word complex vector, probability amplitude, all these things that, if you do quantum theory, you're so familiar with? Let's just ban all those terms for just a moment and, see what quantum theory looks like. And, I found the exercise writing this up to be kind of refreshing. And I tried to make it, relatively self-contained. If you're familiar with, matrix multiplication and maybe a conditional probability or two, you should be able to follow along. And so this is sort of an exercise in, what does quantum theory look like from this point of view?
Matthew, quick question, if you permit it. Okay to?
Yeah, please.
Nathan here, just joined for the first time out of San Francisco.
Hi.
So there's not to get off track, and perhaps you're going to address it, or you did before. If the world is quantum, how come we're not? I mean, if the world is probabilistic, quantum, I'm assuming those two may be equivalent to some degree. How come we're deterministic, Homo sapiens are? Is that a...
I mean, this is a deep question. Do we expect...
I'm not going to you to answer it now. I'm just joining in.
Sure. No, I mean,
first time, because I ran into it the other day. I never thought of it. It occurred to me it's interesting. How come Homo sapiens didn't evolve? uh, more probabilistically. We're terrible at probability. We barely have a taste of it, right?
Well, I think we have probabilistic intuitions. I mean,
Right, intuitions,
we
but not
have,
as strong as deterministic ones. We're basically deterministic creatures, right? The classical being an approximation. Why do we approximate?
well,
This is what
humans,
I wanted
I
to stress.
mean, practically speaking, it's not always so easy to predict what humans will do. But I think, to your point, it's like one expectation that you might have of a physical theory is to sort of describe or contain the users of that theory within it. So you kind of want to like, well, what's, here I am. I mean, that's a quantum system. That's a quantum system. I'm a quantum system. What happens when I put myself in the picture? And I'll say, towards the end of today's little lecture,
Okay.
I get, a little bit into some of the perhaps paradoxes that you get into when
Okay.
you do that. I would say, with regard to cubism, as I say, there's sort of two strands. One is a very pragmatic, almost positivistic approach, where you just want to say like, quantum theory is a kind of probability theory or a decision theory. Such things like a decision theory already assume there's like an agent, like there's somebody out there, whatever they are, going to be agnostic about what they are, and they're trying to make good decisions, and they're gambling on the outcomes to quantum measurements and so forth. And how should they make their bets? And then there's like a sort of a deeper question about what is an agent, and that's like a very tricky issue. Different interpretations of quantum mechanics try to discuss that, in different ways, right? Like the many worlds approach, of course, is like, well, of course you're a quantum system. And so, when you measure something, there's two versions of you that, one sees spin up, the other one sees spin down, and so forth. So you're sort of in the picture. But yeah, no, it's a deep issue. Whether we as humans are deterministic is a tricky issue. I mean, certainly, there's reason to believe, I mean, the standard line, right, is, brains are hot and messy and decoherence will be relevant and so forth. But, at a fundamental level, I think it's an open question and a good one.
Thank you. Continue, please.
Sure. Yeah, what I wanted to say a little bit by way of introduction is just that we're not going to like prove anything today. Well, maybe a little bit. But as I say, in a lot of the great expository papers on cubism, a lot of what goes on is like relating the probability formalism to the standard formalism. And so like in theory, everything that I tell you today can be derived. I mean, unless I've made some grave error, can be derived from the standard formalism. Like it really is nothing other than standard quantum mechanics. Like there's no new magical thing that I've added. But for the sake of exposition, like I'm not gonna show you how it relates to the original formalism. In the sequel to this meeting, next week or the week after that, I will do that basically. But I thought as an exercise, it would be interesting to just sort of like forget the normal formalism and just sort of like look at quantum theory from this point of view. And so, if you're familiar with the subject, in the back of your mind, of course, you'll be thinking about the standard way of thinking about things. And also, I'm like, if in the course of it you have questions like, oh, what is this or whatever, I'm happy to break my rule about not ever mentioning a complex vector and relate that to you if you're interested. So yeah, the conceit is something like, you're on a transatlantic flight and the plane goes down and you wake up on a desert island and lo and behold, there's like a physics lab and there's like a bunch of sources of quantum systems and a bunch of measuring devices that you can throw quantum systems into with lights on them that blink, and you have a pad of paper and a pencil and you can, collect statistics. And like on the desk when you walk in is like a user's manual. and it says like, hey, you want to like make good predictions about, you know, what your measuring apparatuses are going to measure. Here's some rules. I'm not going to tell you where they came from or whatever. Like, just here it is. Tell me what you think. So that's sort of the game that we'll be playing today. But as I say, it should be relatively self-contained. And you know, I tried to hit, you know, most of the main important things that you have to know. So unless there's any other questions, we'll begin. Well, I should say, well, if anyone has any questions, please ask as I set this up. Just to remind you, if you don't already know, this website here, heyredhat.github.io, is where I post the notes for these meetings. And today's is right here. Welcome to the lab. So if you like to follow along at home or, you know, consult this later, here it is. I'll drop a link to this in the chat. I actually have a much prettier version with better font, which I will be using. Okay. All right. So let's do this. Welcome to the lab. So in your lab, you have a collection of sources and a collection of boxes. Each box has an input port and an output port and some number of lights, more than one, on the box. So your sources spit out stuff, who knows what it is, and you can direct the stuff into the input port of a box, and the stuff will come out the output port. In general, will be different than when it went in. When you send stuff into a box, sometimes one of the N lights on the box will blink. You can take your sources and your boxes and you can arrange them in whatever complicated pattern you like. You have 7 different sources going into these boxes, which go into those boxes, which go into those boxes. And the question is, can you predict the pattern of the lights that blink? So first, for each box, figure out which sources always spit out stuff that makes the light blink. First thing, basic. And we'll say that a given source then is compatible with a box B if whenever you send stuff from that source into that box, one of the lights blinks. We can characterize the relationship between a compatible source and a box using a probability vector. So given a box, we'll label the lights, say BI, where I ranges from 1 to N. And if you send the source, if you send stuff from the same source many times into the same box, you keep track of the tally of how many times each light blinks, and you divide this vector by the total amount of stuff that you send in, you'll get a probability vector that'll sum to 1. And so we'll be using probability vectors to characterize the relationship between a source and a box. Similarly, we can characterize the relationship between 2 boxes, say column A and B, with a conditional probability matrix. So make a table whose rows are labeled by lights of B and whose columns are labeled by lights of A. Now what you want to do is send stuff completely at random, from lots of different sources into box A, and then direct what comes out into box B and record the pairs of lights that blink. So you're like, okay, B, the first one of B blinked, and then the second of A blinked. Or the third of B blinked, and then the first of A blinked. And for each pair, whenever that happens, put a tally mark in the ith row and jth column of your table. And then finally, divide each column by the total of that column to get the conditional probability matrix. So that'll mean like each column is will sum to 1 after you do that. So suppose instead that we'd sent stuff from a single source into A and then B. So here, when we were coming up with our conditional probability matrix, we didn't want it to depend on the particular source of stuff that we were using. We just wanted to characterize the relationship between the boxes themselves. So we sent stuff from lots of different sources into B and then into A. But suppose instead we'd sent stuff from a single source into A and then B, kept tallies of the pairs of lights that blink, and then and got our matrix, and then like divided the whole matrix by the total amount of stuff that we'd sent in. So you'll end up with a matrix like this, which will give you like the joint probabilities for each of the pairs of lights on boxes B and then A to blink. So if you think about this matrix, the sum of each row will give us like the probability of the outcome BI, or like if it's the first row here, get probability for the first light of B to blink. And the sum of each column will give us the probabilities for the A lights to blink. As I said before, if we divide each column by its column sum, which is a probability of an A outcome, we'll obtain the conditional probability matrix. Therefore, we can think about this matrix as its entries being like the ith jth entry is the conditional probability of BI given AJ times the probability of AJ. In other words, and this is just like a standard thing in probability theory, we can write like the joint probability that the ith light of B blinks and then the ith light of A blinks as the conditional probability of B given A times the probability of A. If we sum each row, as I said, we get the probability of B. And so we can write the probability that like the ith light of B blinks as this sum, where we go over all of the probabilities for A, and we multiply them by the conditional probabilities for B given A. And this is known as the law of total probability. So we can write this little formula in matrix notation. So if we have a little probability vector A, which represents our probabilities for the A lights to blink, we have a probability vector B for the probability for B's lights to blink, then we can go from A to B by multiplying A by this conditional probability matrix, which I've written in this sort of like little bracket notation. Okay, so read this as the conditional probability matrix of B given A.
Quick question, Matthew. Are these sometimes called transition matrices, or is that a different term altogether?
Yeah, sometimes they are. Yeah, like in probability theory.
Okay, okay, thank you.
Yeah, and it'll be like a stochastic matrix as well. And so naturally, you know, if we know the conditional probability matrices for like each pair in a chain of boxes, then we can calculate the probabilities for the lights of like some final box using the probabilities for the lights of some initial box. So if we know the probabilities on the initial box, and then we know the probabilities of like B given A, and then C given B, and then D given C, we can like multiply them all together to get the probabilities that the lights of D will blink. So far, this is nothing other than standard probability theory. Like nothing quantum has happened yet, okay? We can characterize a box B in its own terms by looking at its self-conditional probability matrix. In other words, the conditional probability matrix corresponding to sending stuff into the same box twice. And by the way, I should say, in the interest of making this self-contained and being kind of a fresh look, I have availed myself of some terms which I thought were useful, which you won't necessarily find in paper. So like, I call this a self-conditional probability matrix because that sort of makes sense, but you may not necessarily find that in some of the references.
That's just what we need, Matthews. Yet another name for matrix. Thanks.
For sure. So you have a box B, and then you have another box B. It's the same box, and you send some stuff in, and you get the conditional. You can get the conditional probability matrix of like a repeated box. So we'll call that the self-conditional probability matrix. And looking ahead, we'll call the columns of this matrix the output vectors of B. And if you think about it, it's like this will characterize, like if like the first light of B blinks, then you'll get some probabilities for the lights of B to blink when you send it through B again. And so you can use that to sort of characterize what's coming out of B, given that like the first light blinked, or what's coming out of B, given that the second light blinked, solely in terms of B.
Technically, you mean what's likely coming out of B, right?
Sure, yeah.
Formally, what's likelihood?
Yeah. So this, like, we're going to characterize it by a probability vector, but yeah, for sure. So certain boxes have a very special property, namely that the self-conditional probability matrix is just the identity. In other words, if you send stuff into such a box B, and the ith light blinks, and then you direct the stuff into another such box B, then the ith light will always blink again with certainty. In other words, if you repeat the box, you'll always get the same result. So we'll call these reliable boxes. And in general, it might be the case that boxes are somewhat reliable, but completely reliable boxes have this property. And so we can think about that as the self-conditional probability matrix just being the identity. So to each kind of stuff, we can associate a number D, its dimension. Now, in general, stuff can light up a box with any number of lights. Like the same stuff could make something with 2 lights blink, 3 lights, 4 lights, whatever. That doesn't matter. But each box is only compatible with stuff if the stuff has the right dimension. So how to find the dimension? To determine the dimension, sift through all the boxes compatible with a given kind of stuff. And you'll find that there will be a maximum number of lights D, such that if a compatible box has more than D lights, it can't be reliable. In other words, the dimension D of some stuff is the maximum number of lights possible on a reliable box compatible with that stuff.
Could you do that one more time, please, from the last sentence?
Yeah. So a given dimension D, it's the maximum number of lights possible on a reliable box that's compatible with it. So in other words, if dimension was 2 for the stuff, then all boxes with 3 or more lights can't be reliable for that kind of stuff.
Okay. So it's pretty obvious, isn't it?
Yeah, I mean, well, one of the...
I'm trying to understand it.
This is to be like, quantum theory is often confusing. Is there a point of view from which you're like, yeah, that makes sense? So yeah, I'm glad that, sure, why not? That makes sense. In general, if we repeatedly send stuff from 2 different sources into the same box, I mean, you have a box and you're like, okay, send stuff from the one source, and they have a box, send stuff from the other source, and you keep track of their 2 probability vectors, it's certainly the case that you might get the same probabilities for each one. It could be, you could have two outcomes and you have two different sources and they both give you, 50-50, 50-50 for the lights. But if that's the case, then the box, you could say, can't tell the two sources of stuff apart. Different sources give the same probabilities. We'll call a box informationally complete, however, if each kind of stuff gives you a signature vector of probabilities, so that having estimated those probabilities, you'll never confuse one source for another. Like each kind of source will give you a unique set of probabilities on an informationally complete box. Here's the thing though. For a box to be informationally complete, it has to have at least d squared lights, where d is the dimension of the stuff that the box is compatible with. And an obvious implication of this is that a reliable box can't be informationally complete, and an informationally complete box can't be reliable.
Whoa,
And in some ways, this is the central nugget of quantum theory.
say that again, please.
A reliable box can't be informationally complete. So if you have a reliable box, in general, there will be like stuff that you'll have to assign, the same probability to two kinds of stuff. But as I say, an informationally complete box will give you a signature set of probabilities for each kind of stuff. But because you have to have at least d squared lights for it to be informationally complete, then that box can't be reliable. In other words, you send stuff into the informationally complete box, you estimate probabilities, you use those probabilities to characterize the stuff. But if you repeat the box, if you take an informationally complete box and do it again, you won't necessarily get the same outcome. It's unreliable in that sense. And finally, a comment is that the more outcomes a box has, in principle, the less disturbing it may be to the stuff that goes through it.
What do you mean? What do you mean?
Oh, I'm sorry, say that again?
What do you mean by disturbing? You mean altering it or?
Yeah, that like, in terms of like the difference between, the whatever is described by a given probability vector coming in, and then, you're going to describe what comes out by another probability vector. And the question is, how different are they going to be? We have a question in the chat. For each box, do I presume correctly that the output stuff can be different from the input stuff? Yes, absolutely. So a box may be biased or unbiased. In other words, some of the box's lights may be more intrinsically likely or unlikely to blink completely independently of the stuff that you throw into it. So to determine the bias, throw stuff, from many different sources, completely at random into the box and collect a probability vector for the lights. We'll call it C, the bias vector. And if this vector is the completely even probability vector, 1 over n for n lights, for 2, it'd be like a half and a half, then we'll say that the box is unbiased. And this just means that like, if we're completely uncertain about what went in, then we're completely uncertain about what light will blink. But if we get some other probability vector, then C is going to tell us how the box is biased towards different outcomes. In other words, send stuff completely random in, but we're like, oh man, this first light just blinks, 2/3 of the time, but the other two each blink 1/3 of the time. So that one of the lights blinking is just intrinsically more likely to happen than the other ones. And so we'll say that's like the bias of the box. Either way, biased or unbiased, it'll be the case that if you act with the self-conditional probability matrix on the bias vector, it'll just give you back the bias vector. In other words, the bias vector is an eigenvector. Okay, Now this part's cool. This is where suddenly the quantum part comes in really, like this is like the moment. For each box, we can construct a metric. This is my term, I have to say. I think it's a useful way to think about this. So for each box, we can construct a metric. How to do it? Take the self-conditional probability matrix. In other words, the conditional probability matrix for the same box repeated, and take the bias vector for that box and multiply each row of the matrix by the vector D, where D is the dimension, times the bias vector. So in other words, you have this vector D times the bias vector, and then multiply it by the first row, like element-wise, and then multiply it by the second row, and so forth. This resulting matrix, call it GB, will be symmetric, as will its inverse. And we'll call GB inverse the metric. Why do you do it exactly this way? Well, don't worry about it. Suffice it to say, that's what you do. An aside is that a box can be informationally overcomplete. Like, in other words, to be informationally complete for dimension D, you have to have at least D squared outcomes. But like, what if you had more than D squared? The box could still be informationally complete, but it'll be like overcomplete. You have like extra, like more like redundant information, okay? And note, if this is the case, then G actually won't have a proper inverse. And so just take the pseudo inverse as a reminder for what that is. You take the singular value decomposition of G, splitting it into the product of three matrices, U, D, and V, where U and V are orthogonal matrices. In other words, those whose inverse is their transpose. And D is a diagonal matrix with the so-called singular values along the diagonal. D will have D squared non-zero entries, take the reciprocals of them to form the inverse, and then you can get the pseudo inverse by just doing this. Yes, David.
It's DC. Yeah, you're multiplying by DCB. That looks like a vector.
Yes. Yeah, sorry.
So you're going to get a vector out, not a matrix.
So what you want to do is like take the first row of the matrix, and then you have this vector DC, and then multiply the first row by that vector element-wise. So multiply like the first entry of DC by the first entry of that row, the second entry of DC by the second entry of that row, and so forth. And do that for each row.
All right. And not sum.
Not sum, yeah. So you'll get a matrix.
That's it. Yeah, okay.
And if you think about it, it's like the conditional probability matrices are not symmetric. We imposed by like normalizing the columns that there's going to be some asymmetry. When you do this, you're actually, basically kind of, you're going to get a symmetric matrix, which is the important part here.
You're weighting it, yeah.
Yeah. So this a bit about the singular value decomposition is just an aside. If you're interested, you're really trying to be self-contained here. If you have more than D squared outcomes and you want to calculate the metric, use the pseudo inverse. Okay. Suppose we have, so this is what we can do with the metric. This is the fun part. Suppose we have two sources, okay, SA and SB, each characterized by a dimension D, and an informationally complete box, we'll call it R, with D squared lights. We collect the probabilities A and the probabilities B for these two sources with respect to this box R. And then we could ask the question, suppose I send stuff that's characterized by A into any box. What's the probability that stuff characterized by B will come out? And the metric provides us with the answer. We can write the so-called transition probability which is actually symmetrical. In other words, transition probability for A to go to B or B to go to A is the same. And it's just this. In other words, take your vector A, act on it with the metric, and then act on it with B. So, I mean, technically, A is going to be a column vector, G is matrix, B is going to be a row vector. And so you're going to act with this matrix on this vector, and then take the inner product between B and G on A, and you get a little sum. And so this will be a scalar. And it is the transition probability. In other words, this is the, not to jump the gun, but like this is the Born rule. This is what it looks like here. In general, this transition probability will depend on the number of lights on the box and its bias, and it'll be like proportional to this number. But if this transition probability is like 0, in that case, you don't have to worry about that. And you can just sort of say categorically, like in terms of your expectations, that if stuff characterized by A goes into any box, and you're wondering, could stuff characterized by B ever come out? It won't. And you can say that for any box. And if that's the case, we'll say that A and B are mutually exclusive, like their probability vectors represent mutually exclusive outcomes. And if a box is completely reliable, in other words, if when you repeat the box, you always get the same answer, then all its outcome vectors are mutually exclusive. So any box will determine a metric in this way. And then the cool part is that like if the box is informationally complete, then the transition probability determined in terms of its metric will always agree with the transition probability determined by using any other informationally complete box's metric. In other words, you could have stuff characterized by some reference box, some informationally complete reference box B. So you get your probabilities for source A on B, your probabilities for source B on B, and then you have B's metric. You calculate transition probability. That'll be the same if you had used reference box C and you got, probabilities characterizing A on C, probabilities characterizing B on C, and then you had the metric for C, and you get the transition probability. They will agree for all informationally complete boxes B and C. So we could consider like the self transition probability. In other words, you start off with stuff characterized by A. What's the transition probability that it goes to A? Now, since this is like a probability, this quantity has to be between 0 and 1. I mean, that's what probabilities are all about. If the self-transition probability is 1, then we'll call A pure probability vector. And if the self-transition probability is less than 1, we'll call it a mixed probability vector. And mixed probability vectors can always be written as sums of pure vectors. The idea is that a pure vector characterizes like one kind of stuff, but a mixed vector characterizes uncertainty about which kind of stuff that you're dealing with. So like if, for example, you behind my back fed stuff into this box B from source A like a third of the time, but then like 2/3 of the time you sent stuff from source B in there, and I didn't know that, and I just like recorded naively the probabilities, I would get a mixed probability vector. And if I had like the probability vector for like, oh, I just send stuff from source A and I just send stuff from source B and I characterize it, I get A and B, then I can write this probability vector, the mixed probability vector, as just a weighted sum. Similarly, we have on the one hand pure boxes and on the other hand mixed boxes. And the idea is that the output vectors of a pure box, in other words, the columns of the self-conditional probability matrix, are all pure. And another way to check to see if a box is pure is whether the diagonal of the self-conditional probability matrix is just D times the bias vector. So the upshot of all that is that in the case of a pure box, if you see the ith light blink, you should wager that the stuff afterwards will be characterized by the ith output vector of A. In other words, if you saw the second light blink, then look at your self-conditional probability matrix, look at the second column, and that should be the probability vector that you assign to the outgoing stuff. There's a slight complication in the case of mixed boxes, and we will come to that momentarily. So we've seen how, by means of the metric provided by an informationally complete box, which we'll call a reference box, we can calculate this transition probability between two kinds of stuff that is applicable for all boxes. Similarly, we can calculate the probabilities for the outcomes of any box in terms of two things. One, the probabilities on the reference box, and B, the conditional probabilities between the reference box and the box you're interested in. So how do you do it? So suppose we have a reference box R and another box E, and we have the probabilities for some stuff coming out of a source on the reference box. Call that R, little r. We also have the conditional probabilities for the outcomes of E given the outcomes of R. It's just this conditional probability matrix, E given R. Finally, in terms of ingredients, we have the self-conditional probability matrix for the reference box with itself, R given R. And then just as before, when we were playing around with the metric, we're going to invert that matrix. So we all know, standard probability theory, that by the law of total probability, we can calculate the probability of one of E's lights to blink if stuff characterized by R first goes into an R box and then an E box. It's simply R, which is the probabilities for the stuff on the R box, multiplied by the conditional probability matrix for outcomes of E given outcomes of R. So that's the familiar rule. On the other hand, using this inverse of the self-conditional probability matrix, R given R inverse, we can calculate something else, which is the probability for one of E's lights to blink, supposing that something, supposing stuff characterized by R just goes right into E. In other words, before we were okay, we have R characterizes some stuff with respect to the reference box. And so we're considering the situation first it goes to the R box and then the E box. But now we want to know, we have this stuff characterized by R. What if it just goes directly into the E box? No R box in the middle. We've characterized this stuff using probabilities on R. And since it's informationally complete, you'd think, okay, well, there's got to be a way to calculate, what are the probabilities for the lights of E to blink. And the way you do it is just this. It's the same as, this, which you get from the law of total probability, but you just stick this little matrix R given R inverse in the middle. So you take some stuff, characterize it with reference to this box R, you get this probability vector little r, you act on little r with the inverse of R given R, and then you multiply it by E given R. So since R given R inverse is just the inverse of R given R, so that if you act with R given R on this quantity here, you'll just get back R, little r. And therefore, you can think of R given R inverse on R, on little r, as the probability vector R like pulled back to before the R box was performed, such that going into another R box would recover the original probabilities. From this extended vantage point, think about it like what would have been R, like if it had gone into R, instead enters the E box, characterized here in terms of its relationship to the R box. And this will give us the probabilities for E's lights to blink in terms of R's without assuming that the R measurement was actually performed. We'll call this like a passive transformation. In other words, we're basically saying, like, we have stuff characterized in terms of this reference box, and we just want to switch reference frames, as it were. Instead of describing things with reference to that box, let's describe it with reference to this box. Like if E and R were both informationally complete, like then we wouldn't lose any information. We just take, okay, we have these probabilities for the lights of R, and then we can use this formula to calculate the probabilities for the lights of E. It's the same stuff.
Question.
Yes.
Matt, I'm trying to relate this to the real physical world. Could you interpret the R box as being initial conditions?
Well, I mean, the idea is like you have some source of stuff, and then you're, sending it into like a box R that's going to characterize that stuff in terms of probabilities. So I mean, like the source is more like the initial conditions.
Good
Well,
point.
okay, but I'm saying if the initial conditions have some statistical distribution, which would make this compatible with Bohmian mechanics, which I'm always, thinking about. If you say the R box can be related to some statistical distribution of initial conditions, would that be valid?
Well, I mean, like I'm saying,
statistical or probabilistic, distribution.
Right. I mean, like there's many informationally complete boxes out there. So like I could have some source, I could send it into this reference box and get a unique set of probabilities. I could send it into another reference box that's just like different, but like also informationally complete, and characterize the stuff equally well by those probabilities. So I hesitate to be like, they're like the initial conditions because it's like, it's not unique.
But the output of the R box is unique dependent on the input. No?
Well, right. So like so like the each kind of stuff will give you, a unique set of probabilities on the R box.
So that's why I say that the R box could be interpreted as a statistical distribution of initial conditions, which again would make this compatible with Bohmian mechanics, and the whole situation would be.
I mean, I feel like,
deterministic.
well, I feel like the concept of the statistical distribution is kind of like static, whereas like this is like a box. It's kind of like a process. I don't know if that.
Well, we'll see what comes next.
Okay. So like, I'll call this like a passive transformation, because it's really just like switching reference frames, where like a reference frame in this case is like a box. And you can see that like the only difference between using like the standard law of total probability and like this rule for passive reference frame switching is that we stick this extra little matrix in the middle. And so you can think about it like a sort of modification of the law of total probability. And just for intuition, like read this equation as what would have given probabilities R, like little r, on box R, on reference box R, instead gives probabilities little e on box E. So there's a kind of, in a way, the addition of this little inverse matrix here is allowing you to consider like a counterfactual situation. What would have given probabilities R, if you'd said it a bunch of times, into this R box, instead gives probabilities little e if you were to send it into box E. So in between two boxes, it may happen that stuff changes. This will happen. You can capture this change using pairs of identical reference boxes. And so in this way, calculate the result of an active transformation on probability vectors. And the basic principle is that what can happen in between two identical boxes is dual to reference frame switching between two different boxes. So what we're going to do is direct some stuff in a reference box R, transforms, let it transform, and then afterwards send it into R again. And we're going to collect conditional probabilities. In a sense, you can think about it like we're creating like a new box consisting of whatever happens after the first R box, including the second R box. So we'll call this nominal second box, R whatever with arrow. So we'll end up with this conditional probability matrix. So if stuff transforms and then goes into a box, you'll get the same effect as if the original stuff went into a box that's been transformed in the opposite direction. In other words, all of its outcome vectors have been transformed in the opposite direction. This is like a general principle about like perspective, right? Like hold out your thumb, right? Like you can either turn it to the right or you can turn your head to the left. Afterwards, like in both cases, like the relationship between like your head and the thumb will be the same. Okay, it's like I can transform something, the thing in this way, or I get the same result if I transform the reference frame in the opposite way. Therefore, we can think of this R with arrow as R transformed in the opposite way to the stuff. So we're thinking about it like it now not as like a transformation of the stuff in this direction, but as a transformation of the box R in the opposite direction. Therefore, we could use our rule for passive reference frame switching to calculate the result of an active transformation. In other words, if we have some probabilities for the stuff, goes into R, transforms, and then goes into R again, and we calculate this conditional probability matrix, we can multiply that initial probability vector by the inverse of the self-conditional probability matrix by this conditional probability matrix. And this will give us the probabilities for the stuff with respect to R after the transformation, but before the second R box. So this is like an active transformation. In other words, the way we should update our probability vector after a transformation can be thought of like what would have given probabilities little r on R instead goes into R with an arrow. The box evolved in the opposite direction and so gives these probabilities. So you can think about an active transformation as like would, but like in reverse. It's like the same rule, but the sign of it is different, basically.
Matthew,
Yes.
a quick aside. It's a great document we're looking at. Boy, could it use some diagrams.
I should have, yeah, for sure. Diagrams are very time consuming to make.
Right. No, maybe I'll even look at it and throw you a few, see if you like them.
Oh, sure. That would be amazing. Yeah, definitely. That's definitely one of my summer projects to make this even more, humanly consumable with pictures and stuff like that. Yeah, any help that you can offer, I would gladly accept. Thank you. And I should say, just as an aside, just like, okay, if you're thinking about the standard formalism in the back of your mind, right? Reliable boxes correspond to measurements with orthogonal outcomes associated with Hermitian matrices. Each eigenvector, each orthogonal eigenvector is one of those reliable outcomes. This rule that I've just given you for an active transformation is nothing other than the Schrodinger equation. This is what unitary evolution looks like. Similarly, that transition probability is just the Born rule. That's, if you're wondering, this is like how to connect it up with our usual terminology. I'll skip that part. Okay. So a little aside on so-called symmetric informationally complete boxes, which are beloved by the cubists for various reasons. So when it comes to reference measurements, I mean, depending on your circumstances, your goals in life, different kinds of reference measurements may or may not be useful to you. But perhaps the most beautiful kind are the most symmetrical, the SEECs, symmetrically informationally complete boxes. They have exactly d squared pure elements such that the transition probabilities between them are all equal. For d equals 2, there is in fact a SEEC, and we can characterize it in terms of self-conditional probability matrix, and it looks like this. So the columns are the output vectors of this SEEC. And so what this is saying is that if you do R twice, like you have some stuff, send it into R, see what light blinks, and then send it into R again, half the time, you'll get the same answer. The other half of the time, you'll get one of the other 3 answers each, a third of the time. In other words, probability a half for getting the same answer, and then a 1/6 probability for the other ones. We can look at the inverse of the self-conditional probability matrix, which we use to do our active and passive reference frame transformations. Looks like that. And in the interest of being self-contained, little flashback to any linear algebra course you may have taken at some point in your life. Recall how to invert a matrix. The one simple way is to place the identity matrix to the right of your matrix and create an augmented matrix, and then perform elementary row operations. In other words, you can swap rows, you can multiply or divide a row by a constant, you can add or subtract a multiple of a row to a row, and you play this game until you've managed to get the identity matrix on the left. So you start off with the identity matrix on the right, and then you get the identity matrix on the left, and when you've done that, what's on the right is the inverse. Again, I'm assuming you're on a desert island and you just have a pad of paper and a pencil. So you want to be able to calculate this stuff. So a SEEC is unbiased. So for example, if we send this flat, probability vector, multiply it by by R given R, it just comes back to itself. And we can get GR by, as I say, multiplying the rows of the self-conditional probability matrix by D times the bias vector. In this case, the bias vector is just a very simple flat vector, 1/4 all the way, multiplied by 2. So then essentially you're just like multiplying the matrix by 1/2. And then you can invert that to get the metric, which looks kind of beautifully simple. It's got 5s along the diagonal and everything else just -1. And in fact, that pattern sort of continues, for any dimension. if a seek exists, which is not as certain as one would like it to be, by the way. But if it does exist, then these four matrices, which we have had recourse to, in other words, the self-conditional probability matrix and its inverse, and also this matrix G and its inverse, which we're calling the metric, will have these matrix elements. So this is just, the entries along the diagonal, and these are like the off-diagonal entries, and you see they just depend on the dimension. And in fact, like looking at the metric, like this pattern always continues. In other words, all of the off-diagonal elements will always be -1, and you'll just have some different thing along the diagonal, which will be d times d plus 1 minus 1. And so when d is 2, that's 5. And because that's like so simple, we can make, some kind of like dramatic simplifications to like say like our transition probability rule. So, we can write the transition probability between like A and B like this, where, AI, BI, those are the components of the probability vectors. And, in the case of D equals 2, we can plug, 2 into that, and we get this. And so we can say that, like, if we're interested in the case where the transition probability is 0, it's just this. 5 times sum over I of the ith entries of A and B multiplied together, all summed, is equal to go over all the i's and j's, look when I does not equal j, and multiply AI times bj and sum it all up. In other words, the transition probability is 0 if, when you send A stuff and B stuff into the reference measurement R, you're likely to get different answers 5 times more often than you get the same answer. Kind of makes sense. In other words, if the probability of different lights blinking when you send A and B into a seek in D equals 2 is 5 times the probability of the same lights blinking, then you ought to assign probability 0 for A transitioning into B and vice versa for any box. And of course, that number 5 will be different if you're in a different dimension. Of course, when I say, the probabilities of the same or different lights blinking, I mean like the probabilities irrespective of the orderings of the outcomes. So as an aside, and to sort of motivate something we're about to talk about, namely entanglement, let's just digress slightly on the tensor product. So it's sort of just a linear algebraic fact that if you could rewrite this, act with a metric on B and then multiply inner product of A and B as this, where we take the tensor product of A and B and dot product it with the vectorized version of this matrix, where like the vectorized version is just, take the matrix and lay its rows all in a line, okay? Just kind of unwind the matrix into a vector. So for, intuition about the tensor product, suppose there were like 4 possible outcomes and you recorded this sequence of lights from like your 2 boxes A and B. And it was like, okay, you get 1, first light blinks, second light blinks, third light blinks, and for B, you got first light, third light, etc. So just considering A, we have half of the time we have 1, a quarter of the time you have 2, a quarter of the time you have 3. And for B, you have a quarter of the time 1, half of the time 2, and a quarter of the time 3. So that's considering like A and B in isolation. We can then consider the tensor product of those probability vectors A and B. So here I've just arranged these numbers into a vector, arranged these numbers into a vector, and I tensor them together, which, recall, just means take the first entry of this guy and multiply it by each entry of the other guy, and those form the first 3, and then take the second guy here, multiply them by each of the 3 entries, then, okay, you get 9 entries in total. So that's the tensor product. But like you can get the same result directly from like this table of outcomes by considering the outcomes in such a way that their ordering doesn't matter. In other words, pair each actual outcome of A with each actual outcome of B, and you'll get a data set of 16 pairs. In other words, okay, you have 1, 1, 1, 2, 1, 2, 1, 3. You have 1, 1, 1, 2, 1, 2, 1, 3, 2, 1, 2, 2, 2, 2, 2, 3, and so forth. And if you then calculate the probabilities for each like pair in this list, you'll get the same probabilities from before, where we just like considered the probabilities for A independently of B and then tensor producted them together. If you're familiar with the tensor product, that is well known to you, but I just want to like emphasize that when you're like tensoring them together, we're considering them, these outcomes of A and B, like irrespective of how they're ordered in time. And then of course, we're going to consider, the interesting case when we, are paying attention to the order coming up.
Irrespective of order of time, is that a property of tensors or of this given situation using tensors?
Well, it's a property of like when you just like take the simple tensor product of two probability vectors.
Okay.
Like in this, in the standard formalism, right? It's like you tensor stuff together and those will be like separable states, but you can get entangled states by like summing tensor products together. But like just the bare tensor product is separable in the sense irrespective of the orderings of the outcomes.
Okay, thank you.
A little bit more about seeks. It's just a very pretty geometry. So probabilities, as we know, are between 0 and 1. And so we were able for a seek, because of its very simple form, we were able to write the transition probability like that. And we know it has to be between 0 and 1. And so we could do a little algebra, a little simplification, bip, 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 and eventually write this as given two probability vectors A and B, the simple dot product between them has upper and lower bounds. Okay, it's got to be greater than 1 over d times d plus 1, and it has to be less than 2 over d times d plus 1. In particular, if we consider like the self-transition probability, in other words, like given a vector A dotted with itself, that has to be less than 2 over d times d plus 1. And therefore, the norm of this vector has to be, oh, I should have said less than. So be less than the square root of that. So this is like kind of interesting. Normally the only like restriction on probability vectors is that they have to sum to 1. But for a seek probability vector, it's also the case that the sum of the squares of the elements is bounded, okay? And like we have equality in this relationship in the case of a pure vector. So in a seek representation, a set of seek probabilities, the length of any pure probability vector is a constant, like relating to the dimension. And therefore these pure vectors live on the surface of a sphere of that radius, okay? And mixed vectors live within the sphere. So that's kind of interesting because it's like normally, probabilities, they sum to 1, hence they live in the so-called probability simplex. But for these very special reference measurements that we like, called seeks, the pure probability vectors have this additional restriction that they are points on a sphere.
Whoa, that's the Bloch sphere, right?
Yeah, well, it's very related to the Bloch sphere. Yeah. Yeah, we'll come to that momentarily. So for d equals 2, you can think about this sphere of pure states as inscribed in the probability simplex. So like it just touches like the edges or like the faces of the probability simplex. But in higher dimensions, like this sphere kind of bubbles out of the edges of the simplex so that like not all of the sphere is contained within the probability simplex. So that the outcomes vectors of a seq form a mini simplex whose vertices are pure states that like lie on the surface of the sphere in just the part of that sphere that's contained in the larger probability simplex. And one implication of all this is that a seq probability vector won't have an element that is greater than 1 over d, and like the total number of 0 entries can't be greater than d times d minus 1 over 2. And if we have a seq, then our rule for passive / active reference frame shifting, in other words, our modified law of total probability, takes a kind of simple and elegant form. Instead of writing it like this in the sort of matrix notation, it just ends up being this, where here P E given R, this is a conditional probability for the ith light of E to blink given the jth light of R. Here's the probabilities for the R, take a sum over J, et cetera, et cetera. And in the special case where E is a reliable box, having mutually exclusive outcomes, this formula simplifies even more, where it's like, this part, oh God, this part is just the law of total probability, and we're just sort of stretching it and subtracting 1 from each of the elements. Kind of crazy that works, okay. All right, so now we're actually gonna get an example, and indeed, we're gonna see this connection to the block sphere. So as I've said, for a given dimension D, there's gonna be information complete boxes with at least d squared elements. And these single boxes can be used as reference boxes to compute probabilities for what will happen if your stuff goes into like any other box. That's why we call them reference boxes. But as I say, the sort of central paradox here is that because these boxes are informationally complete, having d squared outcomes at least, they have to be unreliable, because a reliable box can have at most d outcomes. On the other hand, we can achieve informational completeness using reliable boxes, but this is going to require sending stuff from the same source into multiple reliable boxes. We can't use just one. And then the probabilities altogether will characterize the stuff. So in the case of d equals 2, we'll consider 3 boxes, x, y, and z. Yes, they are those x, y, and z. Stern-Gerlach, okay. Each of these boxes has 2 lights, and we'll label them up and down. Now, these are all reliable boxes, and hence their metrics are just the identity matrix. And yes, if we, were playing the game of assigning probability amplitudes and using complex vectors and Hermitian matrices and stuff, we would be like, oh, X, Y, Z, the Pauli matrices. Okay. None of that. Instead, we're going to describe these boxes in terms of their relationship to a reference box. So I've chosen a seq in d equals 2 as 4 outcomes. And so we can fully describe these XYZ boxes in terms of these conditional probability matrices. So here's the conditional probability matrix for outcomes of Z given outcomes of R. So this little rectangular matrix tells us the probabilities, that a Z box will give up or down for each of the seq outcome vectors. So for example, if you send your stuff through a seq, this particular seq, and the first light blinks, then you should expect that the first light will blink in the Z box. If the second light blinks on the R box, then you should expect that the first light on the Z box will blink 1/3 of the time, and the second light on the Z box will blink 2/3 of the time, and so forth. Given some probability vector with respect to R, we can, calculate the probabilities for Z outcomes like directly, like without having actually done this intermediate R box using our modified law of total probability. So we have little r probabilities on the reference box, hit it with inverse of the self-conditional probability matrix, which in the QBIS literature, I should say, is often called the Born matrix. And then we hit that with Z given R. In contrast, looking at this matrix, this is characterizing the stuff that comes out of the Z box in terms of the R box. So in other words, if the first light of Z blinks, and then we send the stuff into R, we're gonna get, first light half the time, And if the second light of Z blinks, we get down, and then we send it into R, you'll get these probabilities. And note that actually just for convenience, I've chosen a seq such that one of the outcomes is in fact one of the outcomes of Z. So hence you have this, 1, 0 here. And you notice this column is just one of the seq output vectors. So, okay, and so similarly, you can characterize this Y box and the Z box, and here are the numbers. And remember, if we knew the probabilities for the lights of Z to blink, we could calculate the probabilities for R's lights to blink. And, because Z is a reliable box and hence its self-conditional probability matrix and its metric for that matter are the identity, there's really no difference between the law of total probability and the modified law of total probability. This just disappears, we just have that. So X, Y, and Z are very special. If we look at the conditional probability matrices for, X given Y, Y given X, Z given Y, et cetera, et cetera, et cetera, which by the way, we can calculate like that, they will just give us this matrix. In other words, if something comes out of an X box and you send it into another X box, you'll always get the same answer. It's reliable. But if you send stuff through an X box and then a Y box, you're going to get up or down, light 1 or light 2 blinking each half the time, equal probability. Similarly, if you'd send it to X and then Z, or Z and then Y, for any pair of X, Y, and Z where they aren't the same, you're going to get completely even probabilities. So therefore, these 3 reliable boxes, X, Y, Z, each associated with 2 mutually exclusive outcomes, are also unbiased or complementary with respect to each other. So suppose we assigned a valuation, a number, to each outcome of our 3 boxes, X, Y, Z. In other words, we have up, we have down, that's light 1, that's light 2, and we'll assign the number 1 to this and the number -1 to that. And so we could create a little weight vector, call it lambda. Lambda because these, in the normal formalism, are the eigenvalues of the Pauli matrices. But let's forget about that. We can then assign an expected value of X in terms of our reference probabilities. So the expected value of X is just 1 times the probability of X up and -1 times the probability of X down. And so we can calculate that in terms of probabilities on the reference box by taking little r, hitting it with the inverse of the self-conditional probability matrix, aka the Born matrix, hitting it then with the conditional probability matrix for X given R, and then inner producting with the weight matrix. And so, as you may know, stuff for D = 2 can be fully characterized by the vector of expectation values, x, y, and z. And just as in the seq representation, pure states live on the surface of a sphere, now in 3 dimensions. So it's, you know, the seq representation with its spheritude is like and indeed related to the block sphere representation, but not exactly the same. In the case of the seq representation, you know, we have a 4-dimensional vector that lives on the sphere. Here we have a 3-dimensional vector, and the pure states live on a sphere. And similarly, mixed states live in the interior of the sphere. And geometrically, x, y, and z each have 2 outcome vectors. And in each case, the 2 outcome vectors correspond to antipodal points on the sphere. And together, those 6 points fix 3 orthogonal axes. That's the block sphere, which we know and love. And again, like in a kind of interesting echo of the issue we were talking about before with the seqs, and there's like a probability simplex, and then the sphere, and then the seq states form another simplex where the vertices live on that sphere. If you calculate the XYZ vectors corresponding to our seq outcome vectors, you'll find they'll make a tetrahedron that fits snugly in the sphere. So you can think about the outcome vectors of our seq reference box as corresponding to 4 points on the block sphere that form a tetrahedron, a regular tetrahedron. And indeed, like a seq box for a given dimension is not unique. And in this case, for d equals 2, there's a whole sphere's worth of them, since rotating the tetrahedron as a whole won't change the angles between the vectors. And so if you find 2 seqs in d equals 2, such that they give different probabilities for the same stuff, then you know they must be related by some 3D rotation. And you know, we've discussed how to calculate the so-called transition probability in terms of, you know, a reference box, maybe a seq, using the metric. In this case, there's a beautiful kind of geometrical way of getting that same number. So if you have 2 kinds of stuff and you've been able to assign 3 vectors, like XYZ vectors, to them, call them A, XYZ, and B, XYZ, you can simply calculate the transition probability between them like this. Take the dot product, the inner product of A, XYZ, B, XYZ, add 1 to it, and divide by 2. And this means that if 2 points are antipodal to each other, they will have 0 probability of transitioning to one another. And finally, in terms of like the particular d equals 2 seq that I've chosen, the XYZ coordinates take this kind of simple form. So P1, 2, 3, and 4 are the seq reference probabilities for your stuff. And you can take these sort of linear combinations of them and get your point in 3 space. I'm going to skip this section because it's sort of an aside and move on to entanglement. Although I could pause for a moment and ask if there's any questions as well. So, well, just as a preview, we'll talk about entanglement for a bit. I'll give another sort of concrete example, and then we'll sort of reach the climax, and there'll be some meditation about a little more philosophy. You'll see what I mean. Okay. So we can consider correlations between the lights of 2 boxes, where in fact we keep track of the order in which we feed stuff into the boxes. In other words, as we feed stuff into A and stuff into B, we can keep count. You know, you could have, you sort of pair off the stuff and you're like, okay, send the first thing into A, second thing into A, third thing into A, and the first thing into B, the second thing into B, and so forth. And keep track of the order. And then I can assign probabilities to like each combination of outcomes of A and B. So I can get the probability that, a first light of A and the first light of B blinked, probability that the first light of A and the second light of B blinked, and so forth.
Matthew,
yeah.
a quick question before you jump into entanglement. I'm noticing something, perhaps you can confirm it or otherwise. Up to now, one of the points you're making is this approach with the 6 and the cubism is analogous, correlates to your traditional approach you might find in Mike and Ike, right? Like you got the block sphere, you got, the Gerlach experiment, you got entanglement, you got tensor products. So they're very much, what's the word, aligned or?
Absolutely. You can think of it like it's, this representation is just like
representation, that's the word. They're equivalent. Is that what you're trying to point out? One of the things you're trying to point out here, Oak's term?
Absolutely. They're completely equivalent. In a way, this is just like a reference frame switch in itself. Okay. It's completely equivalent, mathematical like reformulation of the standard theory. Yeah, for sure. Because it's like basically like in the standard theory, we can sort of represent like all of our information or whatever about a quantum system in terms of D numbers. And those D numbers are complex numbers. They're probability amplitudes. Okay, and using those, we can calculate the probabilities for all the experiments we might do. But we're like foregoing that. And instead, we're going to describe things in terms of the D squared probabilities for informationally complete boxes, which in the standard formalism correspond to positive operator valued measures, if you're familiar with this concept. The basic idea being that you're considering what happens when you take a quantum system and you entangle it with a quantum system with a larger or greater dimensionality.
So it's fair to say it's like the same play, just different, dramatized personae, just different actors in different uniforms.
Yeah, absolutely. And my hope is that, when you learn quantum theory, initially it's so strange, you're trying to wrap your head around, what does it all mean? You have these special kinds of matrices with these symmetries and these unfamiliar vector spaces. And I think there's a tendency to like hypostasize or substantialize or like treat those as like real things, but they're really just mathematical representations. And they're not the only way, and maybe not even the best way of describing the theory. Now, of course, probability amplitudes are really, really useful for something, which is that you can add them together and you'll get interference. Like that's the whole point of probability amplitudes, right? You have a complex vector and you add it to another complex vector and it cancels out. So that interference is something that the standard formalism like makes blindingly obvious. It's like throwing it in your face.
Right.
Here, that's de-emphasized. We're not seeing so clearly, okay, how does the interference come in? But instead we see other things. We see how there's this sort of like interesting interplay between, reliability and informational completeness on the other hand. And that these sort of, there's a sort of counterfactual structure to the theory.
But here you're not making a claim, or are they? I'm just not aware of it. I acknowledge and recognize the importance of the probability amplitude, but you're not claiming also that it's real or not. That's an independent, altogether different issue.
Yeah, right? That's a whole other question. Yeah.
Right.
Totally.
This goes with either way, right? It would fit with either. Okay.
Yeah. As I said, like kind of in the meeting description, this is equivalent to the standard formalism, so that the amplitudes, the complex numbers, they're all there. They're just hiding. They're like under the surface. They're under the hood. And,
whether they're real or just a tool is a totally independent question.
Yeah, that's exactly. Yeah.
Okay. Thanks for that aside.
For sure. And, and if you just stick with the standard formalism, as I say, I think there's a tendency to treat them as real because you just get so used to working with these objects and it just seems like that's what it is. But, trying to like look around, see around the usual way of talking. But yeah, great question. Thank you. okay, so we got joint probability vectors. Okay, so we can send some stuff into two boxes and keep track of the joint probabilities that like the first light of A blinks and the first light of B blinks and so on and so forth. Now, as we noted above, just if we have some like probability vector A and a probability vector B and we tensor them, that'll give us the probabilities over pairs of outcomes in such a way that like the order doesn't matter. And like if that's the case, where this joint probability vector is just like the tensor product of some A and some B, then we'll call this joint probability vector separable. Probabilities for the individual outcomes of A and B aren't different from what you would have gotten if you hadn't kept track of the ordering at all. But in general, if you do keep track of the ordering, then this joint probability vector can represent, correlations, like in the case that the individual outcomes of A and B depend on each other. So take this joint probability vector and rearrange it into a matrix. Okay, so like kind of divide it up, row, 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 okay? Such that the rows are now labeled with lights of A and columns are labeled with the lights of B. If you sum each row, you'll get a vector. We'll call it, probability of A given AB. The standard probability term is like this, like the marginal vector. And if you sum each column, you'll get a vector B given AB. And these are like the partial probability vectors for what went into A on the left and B on the right, considered independently of each other. So like they may be correlated, but we can just consider them individually. And you can use these sort of reduced vectors to calculate the probabilities for stuff on the left or for stuff on the right, considered independently of each other. So it's like if you had some stuff and you set it into two boxes, you calculate these partial vectors, you can then use those to calculate the probabilities of what will happen if you send the stuff on the left into a bunch of other boxes and you're just ignoring what happens on the right and vice versa. So it's a nice fact that this whole formalism with the self-conditional probability matrices, aka the Born matrices, and this metric business, they respect the tensor product. So that, if you have two boxes A and B, then G of AB is just GA tensor GB. And if you have two vectors, A and B, with respect to some boxes, then if you consider the boxes together, then the joint probability vector is just the tensor product of the probability vectors. Moreover, if you have A and B, then like the self-conditional probability matrix of A tensor B given A tensor B is just A given A tensor B given B. Okay. But interestingly, if A and B are informationally overcomplete, then this is not true for the inverse. So you actually have to like take the inverse all over again. In other words, if you have like the metric of A, in other words, G inverse of A, tensored with G B inverse, that's like not going to be G inverse of AB. Just whatever. Kind of interesting. Okay, anyway. So using like the joint metric for like two boxes, we can calculate the self-transition probability. And recall that this is 1 if a joint probability vector is pure, or any probability vector is pure. So we can sort of calculate the purity of the joint probability vector. We can also calculate the purity of the partials. And if the overall joint probability vector is pure and the partials are pure, then we're definitely dealing with a separable state. The outcomes of A and B won't be correlated in their ordering. But we can have this interesting situation where the joint probability vector is pure, but the partial probability vectors are mixed. In that case, we'll say that the joint vector is entangled. In other words, what appears as one kind of stuff, considered as a whole, has parts for which it is uncertain what kind of stuff it is. Correlations across the whole, yet freedom in the parts. And as an aside, we can obviously consider the tensor product of however many boxes you like, A, B, C, whatever. And when you reshape the joint probability vector into a matrix, you'll get some like rectangular matrix. So if you had A, B, C, you want to reshape it into a matrix that has as many rows as A's lights and as many columns as the number of B's lights times the number of C's lights and so forth. Okay, so now let's work out like a cool example, classic example, but in this formalism. So consider this joint probability vector with respect to the tensor product of two seeks in dimension 2. So we'll call the two boxes, they're both seeks, we'll call them A and B, just keep them apart. Could have used L and R for left and right, maybe that would have made more sense. Whatever. So here's the joint probability vector. And here are the marginals or partial probability vectors for A and for B. And we notice, first of all, that these partial states are states of maximal ignorance. Completely flat probability vectors, who knows, each a quarter. Nevertheless, if you look at this, the rule is that if you got, say, outcome AI, say A0 or A1, whatever, you should assign probabilities to outcomes Bj using the ith row of this matrix. Similarly, if you got outcome Bj, you should assign probabilities to outcomes of AI using the jth column, normalized. So we can see that the outcomes of these two boxes are anti-correlated. In other words, if I got this first outcome of A, then I would assign to B this row, normalized as a state. And so the probability for the first light of B to blink is 0. So in other words, if I have some stuff, some joint stuff that's characterized by this joint probability vector, and I send it into my two seeks, the same light will never blink. That rule that I just mentioned, where you're like, okay, if you get outcome I, you should assign probabilities to B using the ith row. And if you get outcome B, J, you should assign probabilities to A using the jth column. That's a special case of a more general rule that bears an interesting resemblance to the transition probability. So suppose we have some joint stuff characterized by PAB. And we throw the stuff on the left into some other box. And we find out, okay, we got to assign probability vector A to it. So we had this joint state, it's been characterized, whatever. Nothing else has happened to it. All we know is like, okay, we've got these probabilities for it. And we do some box on the left and we end up assigning probability vector A to it. How should we update our expectations for B on the right? You use this formula. So the numerator is you take this vector A, which is like the state that you've assigned to the stuff on the left, you hit it with the metric, and then you multiply it by this matrix, which, as I say, is the matrix formed from the joint probability vector. And then the denominator is just the transition probability that the partial on the left goes to the state that you know the left ended up in, which is A. Symmetrically, if you had your joint stuff and then it turned out, oh, okay, the stuff on the right ended up being described by probability vector B, and you want to know how should I think about what's going on the left, you do this. So, you sort of act on the other side. So you take, the joint probability matrix, hit it with the metric, and then hit it with the, in this case, like a row vector, which is B. And similarly, the denominator is just the transition probability for the partial state of B going to the state that like B ended up in. And if you want to calculate like how you should update the joint state, you have this. So I mean, just like in terms of the usual formalism, just like allude to it, this would be like, okay, you've assigned some like entangled, complex vector, like, in the tensor product of your two Hilbert spaces. And then, you form like a projector onto a certain state, say on the left. And then you tensor that projector with the identity, and then you project, and then you renormalize. Okay, it's like that. But that's what this looks like here. So returning to our XYZ boxes, I noted before we have this sort of simple relationship, at least with a particular seek that I chose, between the seek probabilities and the XYZ expectation values. You can see that they're just linear combinations of each other. So we can represent this transformation as like a linear transformation T. So acting on a vector of our seek probabilities, this will take us to a vector of our XYZ expectation values. T times transpose is equal to 12 times the identity in this case. So we're going to form an inverse for T, which is just 1 over 12 times T transpose. So T times T inverse is just the identity. And then we can go in reverse. So like given our XYZ coordinates, we can hit it with T inverse, and we'll get this, which is now the seek probabilities expressed in terms of the XYZ coordinates. But there's a catch. Note that if you add these up, it'll give you 0. Which is related to the fact that the Pauli matrices are traceless. So you can fix this by just adding the flat probability vector of all the quarters to it. And then this will sum to 1. And then you can express the seek probabilities as just that. And you can check that this times that just gives you back your XYZ coordinates. Like in the standard formalism, it's like you get your XYZ expectation values, and then you can like recover the density matrix by multiplying, the X times Pauli X, Y times Pauli Y. Maybe there's a factor of 2, like a half in there somewhere. But then you also have to add in the identity matrix. And so that's really where that's coming from. To connect it up, if you're familiar with the usual formalism. Okay, but here's the point. Here, we've been able to represent our seek probabilities for a qubit in terms of XYZ coordinates. So, and what's nice here is we have left like XYZ undetermined. I mean, they're just variables, right? So suppose we end up assigning, PXYZ on the left. Like we started out in this like anti-correlated joint probability vector, and then it ends up for whatever reason we decide, oh, on the left actually it's PXYZ. What should we infer on the right? So we just use the formula. So you have PXYZ, which is just this vector. We hit it with the metric for that seek for A, and then we hit it with the joint probability matrix, and then that's the numerator, and then denominator is just this transition probability between the partial, which in this case was just the flat vector, times the metric times PXYZ. Down here, this ends up just being a half, and you end up getting this. And if you look at this, this is cool, right? Like all that's happened here is all the signs have flipped in front of X, Y, and Z. And so this is just P negative XYZ. In other words, if we assign a vector on the left that's pointed in this direction, then we should assign on the right a vector pointed in the opposite direction. This whole time we've been talking about the famous singlet state. That's what this is. Okay. So if a seek tensor product box A tensor B would characterize a joint pair of stuff by this anti-correlated probability vector, and then we update on the left to P, X, Y, Z, and we should update on the right to P negative X, Y, Z, the antipodal point. Recalling that antipodal points have transition probability 0. In the standard formalism, their complex vectors are orthogonal, but forget that. Recalling that antipodal points have transition probability 0, we predict that if we send the stuff on the left and the right through reliable boxes with 2 outcomes corresponding to XYZ and negative XYZ, then they'll always be found pointed in opposite directions, even though which one's up and which one's down will be a coin flip. And this will be true for any choice of X, Y, Z. And that's pretty remarkable, as I'm sure you all know, because, you know, the particular direction along which the vectors are always found opposite couldn't have been determined beforehand, since it depends on your choice of reliable box. I'm going to skip this part, just, you know, for the sake of time, because I want to get to this last section. Well, a further aside, which is just, you know, you can think about, you know, a tensor B, like an A box, and then like a B box sitting next to it, as just a big old box that if, you know, A was compatible with stuff of dimension dA and B was compatible with stuff of dimension dB, then that big old box is going to be compatible with stuff of dimension dA times dB, the product of the dimensions. And, you know, indeed, afterwards, you know, you could send the output of some tensor product box, like A tensor B, into any box that's like compatible, like with the dimension dA times dB. In other words, for example, you could characterize the relationship between a tensor product of reference seeks, you know, where this is actually probably, so this is R for D, for dimension D. In other words, it has D squared outcomes, but it's for dimension D. RD tensor RD, and a reference seek for dimension D squared, which of course will have D to the 4th outcomes. Maybe that was not the best notation. Whereas the outcome vectors of tensor product boxes are always separable. This won't be true for, you know, a general box with that dimension. Okay, so here's like the final section. Thank you all for, you know, sticking with me so far. So let's open up a box and look inside. What is a box anyway? All right. So it turns out that in each box B, you know, you open it up, you know, it's like some box, right? It's got some lights on it, and you like pry it open. What's going on inside? And it turns out that in each box with n lights, there's like a little source of n-dimensional stuff, which we're going to call the memory stuff. And it's like stuff comes into the box, it interacts with the memory stuff, and then, you know, the stuff continues on its way, leaving the memory stuff behind. This memory stuff then, remember, it's n-dimensional. It enters a reliable box, call it M, with n outcomes. And it's these outcomes which determine which light on the outer box blinks. In other words, you can think about it like you can have like an unreliable box, but within the unreliable box, there's actually a reliable box sitting in there, okay? So you have some stuff coming in, kind of interacts with this memory stuff. So you have something that's d-dimensional coming in. The memory stuff, say in the case of an informationally complete box, will have d squared dimensions. They kind of interact, and then this memory stuff of d squared dimensions goes into a reliable box with d squared lights. And it's those outcomes that determine which light on the outer box blinks. It's kind of underneath the hood, these unreliable boxes cash out in terms of reliable boxes, plus an interaction with some memory. Indeed, if you delay putting the memory stuff into this like reliable box M, even after the outgoing stuff is left, you'll find whatever outcome you get on the reliable box will be correlated with the outgoing stuff. And if you took the memory stuff and the outgoing stuff, and you sent them into reference boxes and stuff, and you characterize them with a joint probability vector, you would find that they're entangled. Yeah. Oh, I thought I heard possibly a question. So earlier I said that if you have a box, say A, and you get this self-conditional probability matrix, A given A, and the diagonal is D times C, where C is the bias vector, then that's a pure box. Another way of saying it is that the outcome vectors, the columns, are all pure. Otherwise, the box is a mixed box. And I said earlier that if you have a pure box and the ith light blinks, then the rule is you should update your probability vector for the stuff coming out to be the ith outcome vector of A, which is just the ith column of A given A. So some stuff goes in, the first light blinks, and you want to know what vector you should assign to the outgoing stuff, use the first column of A given A. And that is actually just a special case of the general rule that I gave before about updating partial vectors on the basis of entanglement. In other words, it's just a special case of this rule. And I only bring it up now because in order to talk about this, you need to be able to talk about entanglement. So more generally, if you have a mixed box and the ith light blinks, and you want to know what state you should assign the outgoing stuff, you should employ the overall entangled joint probability vector of the memory and the stuff, condition on the ith light of M blinking, and then update your vector correspondingly using that rule I gave before. So just for simplicity, in the following discussion, we're just going to be considering the case of a pure box, just simpler. After the interaction between the memory stuff and the incoming stuff, as I say, you're going to assign an entangled joint probability vector, such that if you get the ith outcome of M, which is this reliable box that's like querying the memory, then you should update your probability vector for the stuff to be the ith outcome vector of R of B. That should be a B. Okay. And like, as we've seen, it's for this reason that you can infer from the lights, like what vector to assign to the outgoing stuff, which you already knew. But now that we're actually considering like the memory stuff, which is like entangled with the actual stuff that you send into it, you could contemplate doing something else. In other words, you don't have to send the memory stuff into its special little memory box. That's a reliable box with D squared outcomes that makes the light blink. You could send it into any old box you like, right? Like let's say you send it into some pure box Q. Afterwards, you'll end up characterizing the memory stuff with some outcome vector of Q, and then you'll update your probability vector for the outgoing stuff using the general rule that I gave before with the metric and the joint probability matrix and so forth. Similarly, if you, send the outgoing stuff into some other box, call it some pure box P, and observe what light blinks, and you haven't looked at what light blinks over here, like you've just kept your memory stuff on the side, like you haven't sent it into any box, and you send the stuff, the other stuff, into a box P, then using the joint state and the rule that I gave, you'll infer a particular probability vector for the memory stuff, and from that assign probabilities for what will happen if you do send it into M, which is the reliable box associated with this memory. And rather than assigning probability 1 to a particular light blinking, as it would if you just sent the stuff through a copy of the original box, you'll get a spread of probabilities for the outcomes of M. So to say it again, if you send the stuff into B, then from what light blinks, you can infer with certainty the outcome of the M box on the memory stuff. But if you send one or the other, the memory stuff or the incoming stuff, into a different box, different being, in the case of memory, a different box from this M, the memory box, reliable box with D squared outcomes, and a different box for the other stuff. In other words, a different box than B, which is the original box that you sent it into. There's going to be a degree of uncertainty, okay, about the state of the other. What's more, you could think about it like arrange a whole sequence of boxes, okay? But like, open them all up and disconnect the interior M boxes, okay? And, your stuff will go in, it'll go into the boxes, it'll kind of interact with all the memory stuff, but you haven't sent any of the memory stuff into any of the boxes, reliable boxes that are associated with it. Stuff's going to enter the boxes, interact with the memory stuff, and afterwards collect up all that memory stuff and put it side by side without, putting it into any box. So if you then repeat this procedure many times and then send the memory stuff into, reference boxes, characterize them in some way, and you look at the entire joint state of, I've been avoiding word state, for the entire joint vector of the memories, then you'll find that the memories are all entangled with each other. And indeed, you can measure them, in other words, put them into their original, reliable box M in any order you like, and you'll get a consistent story about what happened to the stuff at each box. But then again, as we've seen, you don't have to send the memories into their magical, special, memory boxes that are meant just for them. You could send them into whatever box you like. And then, using the rules that I've given you, you could infer vectors for all the stuff, the outgoing stuff. And note that this will preclude you from telling a story about what happened to the original stuff in terms of the original boxes. Since, for one thing, this stuff is now going to be characterized by probability vectors that, aren't even necessarily outcome vectors of any of the pure boxes that they went through. And, if you can imagine that, but even worse, across time. So here's sort of the finale. Suppose that there's some memory stuff inside you, okay? And when you see a light blink, what this means is that some stuff has interacted with your memory. In other words, put yourself in the picture. Place yourself conceptually or in reality inside, some pure box B as the memory. You are the memory, okay? And now imagine what it would be like for someone outside the box. This outsider saw you and the stuff go into this box, and they're gonna see you and the stuff come out, and they want to predict how you are gonna respond to future boxes, you and the stuff. And suppose that, being asked what you saw is effectively the M box for you. Hey, Matt, what outcome did you see? 1, 2, 3, what is it? So, suppose after, you and the stuff get down to your dirty business inside this box, you come out, the outsider asks, what did you see? What was the outcome? And you say, oh, it was light I. Well, then they're going to predict that the stuff will be characterized by the ith outcome vector of B. Conversely, if they then send that stuff into, if they had sent that stuff into a B box, in other words, a copy of the same box, and they observed light I, then they'll predict that if they ask you what light you saw, you'll say, oh yeah, light I, for sure. On the other hand, if they send the stuff into just like some other box, okay, and then, update on the outcome vector, then they're going to assign a spread of probabilities for what you're going to say about what light you saw. So it's kind of weird, right? Like if they just sent the stuff through a copy of the same box, then and then they see, oh, light 2 blinked, then it's like, oh, 100% of the time, Matt's going to say light 2 for sure. Similarly, if they just asked me, hey, what light did you see? I say 3, and then they go send the stuff through a copy of the same box B, it's going to be like third light. But, if either one of us is sent into a different box or asked a different question, then this outsider is going to have to assign a spread of probabilities to what the other one is going to say. Now, it's not unreasonable, like that this outsider will have some uncertainty about how like you're gonna, or I'm gonna answer this question. You can think about it like you're the memory, and the stuff had an agreement, as it were, written in terms of the outcomes of this original box B. And it's like if the outsider respects this agreement, there's a way of asking you and the stuff questions such that the correspondence between your answers is strict. But there are other ways of asking questions such that the other will appear to have some wiggle room in how they will answer, the shape of which depends on the particular question and the particular agreement. And it's like, if you think about it, if the person outside the box like asks like the wrong question of the stuff, in other words, sends them in some random box, and the agreement was like, oh yeah, like, okay, if I say light I, then it's going to be in that state. If it's in that state, I'm going to say light I. If the person outside the box asks the wrong question of the stuff, there's no way you can agree with it. Like, what would agreement mean on an individual outcome basis if you're asked question M, which is what you agreed to, but the stuff was asked question P? What's perhaps confusing is that, like, in repetitions of the scenario, you collect the probabilities. Like you, the memory, are going to assign probabilities to outcomes of B that like depend entirely on the initial probability vector of the stuff, right? For you, it's like, okay, there's this stuff. You send it again and again to the box, and you like look at it, and you're writing down the probabilities or whatever. And the probabilities that you get, are going to depend entirely on like the initial vector of that stuff. On the other hand, in repetitions of the scenario, the outsider will assign probabilities for how you're going to answer, about what outcome B you observed, that are going to depend on the final probability vector of the stuff. In other words, the vector which they assign to the stuff after whatever box that they sent the stuff into. In other words, it's like you're going to describe this in terms of probabilities that depend on like the initial state of the stuff, and the outsider is going to assign probabilities to how you'll answer the question about what you saw based on the final state of the stuff. In other words, it makes a difference in the probabilities whether you place yourself first person or third person into the picture. We could say, like, when the outsider assigns an entangled joint vector to you and the stuff, it's a recognition that you and the stuff have secured a particular relationship, which the outsider beyond the horizon of the box is not a part of. Nevertheless, like, the assignment of an entangled joint vector is a wager that if the outsider puts U in M or the stuff in B, then they can, with certainty, predict how the one will respond from the other's answers. But if the stuff is sent through a different box P, then you're going to answer, so they predict, in a way that depends on P's outcome. And this is necessarily going to surprise the outsider. In other words, they're not going to be able to predict a particular outcome with certainty. There's going to be a spread, so that like no matter what you say, it's going to come as a surprise, despite them having incorporated all possible information into their predictions. Of course, after sending the stuff into P, supposing that they can then, turn the crank and infer a probability vector for you, the outsider could try to find a reliable box that they can send you through that just happens to have as an outcome vector the probability vector that they inferred for you as the result of them having sent the stuff into box P and gotten that outcome. And then they'd be able to predict the outcome of that box with certainty. And in a way, this would compensate for their earlier choice of P, which if they had asked you M, in other words, what light did you see, would have introduced uncertainty. But otherwise, in terms of M, there's just a fundamental ambiguity for the outsider. As I say, after all, if the outsider, if the stuff isn't characterized by an outcome vector of B, there's no more right answer in terms of M. The outsider can only predict a spread of probabilities depending on how strange the new stuff is relative to the fact that if the stuff were hypothetically in an outcome state of B, they'd have certainty. And I use this word hypothetically to connect it up with sort of what we were talking about earlier, and we were talking about the passive and active transformations and the use of this Born matrix, the inverse of the self-conditional probability matrix. I use the word would. It's like sort of a counterfactual thing. Like what would give probabilities R if you'd send it into the reference box, instead gives probabilities E on this other box. Here with like entanglement, it's like the same kind of thing. Depending on this, whatever state they assign to the stuff, they're going to predict a spread of probabilities for you and how you'll answer. And there's a particular rule to use, and we've seen what it is. And in essence, the way you'll get those probabilities has to do with, as I say, how strange the new stuff is relative to the fact that if the stuff were hypothetically or had been in an outcome state of B, then they would have certainty. As if because the outsider didn't respect the relationship between you and the stuff, the price of doing that was paid in certainty. As if because of their choice of box, there's something missing from the world of the outsider, a gap of subjunctivity, like would, should, could, so that your answer must be to them as much an act of creation as the original light you saw blink. And I use this phrase, act of creation, because this is a favorite turn of phrase of the cubists. Anyway, so that's what I got for you. Here's a little bibliography. This first one here is a good introduction to basically this formalism of using informationally complete measurements and like formulating quantum mechanics in terms of them. And it relates it to the usual formalism. This paper here, Quantum Theory is a quasi-stochastic process theory, will go into even greater detail about how to relate this formalism to the usual formalism. Introducing the Q-plex goes into the geometry associated with the seq representations, with the simplex and the sphere and all that stuff. And then a more general introduction to cubism and its philosophy is provided by Cubism, Quantum Theory as a Hero's Handbook. So thank you for listening, and we can talk a little bit. If you have any questions.
Question.
Yeah.
First, thanks for an excellent presentation, Matt. Very good.
Thanks.
The conundrum you described towards the end seems to me to be what is generally referred to as the Wigner-Friend paradox. Is that?
Yeah, for sure.
Mm-hmm. That one observer doesn't have all the information that the other observer has. But that's his shortcoming. but to me, this whole concept of the Wigner-Friend paradox it relates to the measurement problem. The fact that in a classical measurement, you're assuming that the measuring device and the measurer have a negligible effect on the measurement. But in a quantum measurement, the measuring device and the observer who inserts himself has a dramatic effect. So this, I think this explains the conundrum of why cubists feel that reality is subjective. I don't agree with that. I believe it's a mystery problem.
They don't think reality is subjective. They think that quantum states are subjective probability assignments.
But some of that continue it to say that not all agree, but some believe that the reality itself is subjective. In fact, there was a quote from again. I read Fuchs and Stacy, your last reference. I believe that's the last reference.
Yeah.
And that he says that QM. He says QM is mathematical gadgetry and historical happenstance, but I don't think that's the point I was trying to make. But the point,
like, so sometimes they'll say stuff like measurement outcomes are subjective experiences of the agent.
But that's because the agent is subjecting himself into the system, so he's going to affect the outcome.
For sure. But yeah, I mean that, but I want to emphasize, like, that does not imply that, like, quote unquote reality is subjective. It's just saying, in a way that, like, one aspect of this sort of probability formalism is that there is a kind of distinction between whether you're first person or third person. I mean, you can call it subjective or objective or whatever you want, but at the end of the day, it's like the person outside the box and the person inside the box are just going to assign different probabilities to things. However, you interpret that.
Because the one inside the box is affecting the measurement. This is what Fuchs says. He says cubism is a combination of, I'm quoting now, subjective probability with objective indeterminism. And I can't accept either one. I believe in determinism, but isn't this appearance because of, again, we go back to the measurement problem, that the measuring device becomes part of the system. So of course your a priori prediction is not going to be accurate because you're changing the system by making the measurements.
Yeah, I mean, you're absolutely right. That, like, that is, like, a huge part of it. And, like, this whole game where we modify the law of total probability to do those reference switches, it's like, because these informationally complete measurements are disturbing, we have to kind of, like, pull them back in order to compensate mathematically for that disturbance when we then try to, like, use those probabilities to predict what'll happen in other experiments. So in doing that, like, we're definitely, like, that is definitely the spirit of it. It's like we're sort of solving out, for the disturbance. Now, I would say, however, that, like, that's not enough. Like, the idea that, like, a measurement disturbs the system intrinsically or irreducibly or something. I don't think that's a strong enough statement to get quantum theory entirely. Okay, because, like, there's, like, for example, there's this statement which I just gave you, in this piece, which is like, an informationally complete box has to have at least d squared outcomes. Where does that come from? Because, like, for example, if you formulate quantum mechanics in real vector space, so you have probability amplitudes, but they can just be positive and negative, but not complex, which is just, it's like probability. I mean, it's like quantum mechanics. I mean, you have, like, observables, and you have state vectors and all this stuff, but you just, like, only use real vectors. Then for that theory, informationally complete boxes would have, what is it, d times d plus 1 over 2 lights. In other words, for 4 dimensions, you need 10 lights. It's specifically in the case of, like, where there's, complex vector quantum mechanics, that you need d squared lights. Like, in other words, there are many theories that you could come up with where measuring disturbs the system, and therefore that disturbance in some sense has to be solved out for when you want to make predictions about what would be the case if you hadn't done that measurement. But I don't think that's sufficient to pick out like quantum theory as we understand it in particular. There's like a little bit more to it, you know? And in some sense, it's like, yeah, like why complex numbers? You know, why is that the thing? I mean, as I say, what I've given you today is not enough, perhaps, to be able to answer that question.
Well, complex numbers to me, as an electrical engineer, complex numbers were always a phase difference. That complex numbers are not something exotic. It's just a change in the phase of the wave function. But let me ask you.
Yeah, and as you know, my favorite take on the complex numbers is it relates to the fundamental theorem of algebra. You know, you have relationship between coefficients and roots of a polynomial. You know, that's my favorite explanation. But
well, that's math. But I mean, physically, a complex number is giving you a rotation. That's what, and in fact, it can be expressed as a real number plus a rotation. Any complex number can be. But let me ask you more importantly, what do we gain from cubism over Copenhagen? Neither of which I agree with, but what is the advantage of cubism over Copenhagen? How is it really different?
well, I mean, I would say, just with like reference to what we talked about today, I don't think Niels Bohr would have been able to write this. Like, you know, one of the sort of innovations of the cubists, like at least in terms of the math, right, is to take positive operator valued measures or whatever as like more fundamental in some sense than von Neumann measurements. So like in the world of Niels Bohr and von Neumann and Dirac and blah, 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 you know, an observable was just a Hermitian matrix and the outcomes were the eigenvectors thereof, and you could form the projectors and they're orthogonal and, you know, et cetera. The way, you know, the more general way of thinking, however, is like you have a system, you know, it's like d dimensions. The case of a von Neumann measurement consists in like you take some memory stuff that has like also dimension d, and you kind of maximally entangle it. So then, you know, if this is up, then this is up, and if this is down, this is down. You can then consider the more general case where the apparatus has a fuck ton of dimensions. You know, what if it's like you're looking at a qubit? What if the qubit gets entangled with a 3-dimensional system, a 4-dimensional system, a 5-dimensional, a 10-dimensional system, any dimensional system? And it turns out when you do that, like you can just like extract more information about like that qubit than you can with like an orthogonal von Neumann classic Copenhagen style measurement. And in fact, if your memory stuff has d squared outcomes, as we've seen in this case 4, and those, you know, which, you know, in the case of a seq correspond to these states on the Bloch sphere that form a tetrahedron, then, you know, you create this entanglement such that like you have your qubit and then it becomes entangled with this 4-dimensional system. And then you do a von Neumann measurement on the 4-dimensional system. And if you get the first outcome, then the qubit is at this vertex of the tetrahedron. If you get the second outcome, then the qubit's here. Get the third outcome, it's there. So in other words, that more general framework, and by the way, like you can describe that without invoking entanglement per se. You can describe these generalized measurements as simply some set of positive semi-definite Hermitian matrices that sum to the identity. So like if you had Pauli X and you took its eigenvectors and you form projectors, for up and down, and you added them, you would get the identity. But you could have any number of positive semi-definite Hermitian matrices that might sum to the identity, and those would represent one of these generalized measurements considered solely in terms of the system without considering like the entangled apparatus. So it's sort of equivalent. And so like when you, take that in some ways as like more fundamental, I do think it gives the whole theory a different flavor, right? Like instead of describing quantum states as probability amplitudes on, reliable boxes, instead you're representing them as probabilities on informationally complete boxes, these generalized measurement boxes. And I think, what this makes clear is, like the Copenhagen, Bohr would talk about counterfactuals in some sense, like in the idea that like, when you compare experimental situations, like you can't neglect the actual circumstances and like the apparatus, like the fact that an apparatus that measures momentum and an apparatus that measures position literally can't coexist in the same place. They like exclude each other. Like you can't build a machine that, okay. But I think that, what I hope to do with this is make clear the role of counterfactuals and like Woods, which becomes clear when you consider like, as I say, like equations like this. Like this is really the fundamental one. You have some stuff, you have a reference box R, you characterize the stuff beforehand in terms of some probabilities little r, and then you can use this formula to calculate what would have given probabilities r, little r on r, instead gives probabilities little e on e. And so as you say, the whole point of the wood here is that we're solving out for the disturbance of the measurement. So I feel like that's, I found that illuminating. Like, you know what I mean? Like I felt like that was something which you wouldn't have necessarily thought just from reading Niels Bohr. You know what I mean? At a more philosophical level, I think that like Chris and them would say like, Bohr and Pauli, at the end of the day, I think really did want to avoid the language of subjectivity and, would frame the sort of appearance of an outcome to a measurement as, what's Bohr's line, the result of an irreversible amplification from like the very tiny to like the macroscopic world. And, the point is that like there's some, some sort of process whereby, the quantum world with this uncertainty kind of like becomes classical, and how that works isn't necessarily specified. And then it's left to people like Wigner, and Wigner's friend to sort of point out like the sort of paradoxes associated with that when you then try to apply quantum theory to the person using quantum theory, to like the agent themselves. Cubism, I would say, bites the bullet and is just sort of like, okay, so what? It's a probability theory where there's just a distinction between first person and third person. Is that such a crime? You know what I mean? Like,
So it's still, Cubism is still indeterminate. If you believe in determinism, then you can't accept, you can't accept Cubism just as well as you cannot accept Copenhagen.
Yeah, the general spirit of Cubism is that the indeterminism is the result of the fact that the world continues to be created to this day, and not as the result of our ignorance.
But that doesn't explain determinism versus indeterminism. In either case, the world continues to be created. In fact, the universe could be a giant. Seth Lloyd, for example, believes the universe is just a giant quantum computer. But that doesn't necessarily make it indeterminate or determinate. It depends on your point of view. Mine being that determinism rules the day, of course.
Right. Well, I mean, the idea of the world being a giant quantum computer, I assume that has like a many worlds flavor. I mean, the difficulty there is that like you can have a sort of deterministic theory, but you still have to add in the measurement outcomes by hand. You know, you consider like the giant universal wave function, and everybody's just like still in a superposition of like seeing every possible outcome, and all the things are entangled and so forth. And
What happened?
You to be like, oh, I saw this shit, and like that's how.
What happened before? What happened before conscious beings? And Fuchs also seems to raise doubt that lower mammals, like a dog, for example, is not a conscious being. But what happened?
Oh no, he wouldn't say that. I mean, he at best he would say a dog doesn't necessarily know how to do quantum mechanical calculations.
Yeah, but a dog can make a measurement. Just a lot of people can't do quantum mechanical. But the point is, what was there before there were conscious beings?
Well, I think there's, yeah, for sure. I think there's two prongs to that question. You know, one, I think, is that, you know, we are the product of evolution. And we see the world in certain ways because of that history. I perceive the world the way that I do because I have this body for these reasons. And so, you know, when I think about this cup, I'm thinking about all the ways I can pick it up and drink out of it. Yeah. And, you know, our conceptual way of organizing the world is kind of contingent on who we are in our bodies. And it may be that, okay, the world is how it is, but given the way that we evolved, it looks like quantum mechanics to us.
But wait, there's an important point here.
Mm-hmm.
We look the way we look because of the way the world is. It's not the other way around, which I think you might have been.
Well, sure. I don't mean to, I don't mean to be like radically skeptical about reality. I just mean in playing this game of being like, well, before there were humans, or like, well, before there were conscious beings, it's easy to say that, but it's very difficult to like actually cash out what that means. I mean, to actually kind of roll back the clock and in some sense mentally solve out.
I totally agree there. We
years of evolution.
The next 3 weeks, 24 hours a day, and wouldn't get far on that one. So
yeah,
it's a hard topic. I was just making an observation. I didn't mean to interrupt you. Please continue.
Oh, no, thank you. Yeah, so I think that, you know, any statement about like what stuff was like before, I'm not saying you can't make it. I'm just saying one has a certain responsibility in doing it to like reckon with just how much our perceptions and our way of thinking is contingent and shaped by our history. But I would also say that, you know, one of the things that the cubists are explicit about, and which admittedly, you know, people are not often as sensitive to, is that like there's really two variants of cubism. One is cubism as decision theory. Like if you pick up a textbook on decision theory, there's no attempt really to like define like who's using the decision theory. It's just like, oh, you're someone who wants to make good decisions and not lose money on your bets. Well, here's some consistency conditions on your probabilities. In other words, it's like a way of making decisions, and in itself, it just remains completely agnostic about who's making them. Agent, who knows? It's just there's someone, clearly someone's interested in making predictions. So how should they do it? Okay. So that's the very like pragmatic strain of cubism. And then there's the more philosophical, metaphysical, ontological concern that cubists have, which is to say more about the agent, which is like, okay, well, given that it turns out we have to modify the rule of probability this way and do that and do that, what must the world be like such that it makes sense for agents in this world to use that probability theory? And they are like, will say that they are realists. I mean, they will be like, we are totally realists. We're just not prejudiced about what reality is. We're like not going to assume any particular nature to the subject object split. What's a verb? What is this? What is that? We're going to be completely as like open to possibilities, about what reality is, just constrained by the fact that it turns out quantum theory is really useful. So I mean, again, yeah, these concerns about, what was it like before there were conscious beings? The question is very difficult to answer. And I would say that Cubism is just really beginning to think about how to approach those questions, Like, it's interesting, right? So it's like, over the last 20 years, there's just been a lot of this mathematical reformulation, investigations into the symmetrically informationally complete, measurements, into their geometry, all this stuff. In recent times, there's been an attempt to find inspiration in phenomenology. So, phenomenology being this sort of strain of philosophy that grew up in Europe, mainly, in the late 19th, early 20th century, and associated with, in some ways, I mean, William James is not considered a phenomenologist proper, but he's in there. People like Husserl, Heidegger to some extent, Merleau-Ponty, a little bit of Sartre. There's more recently been an attempt to, try to relate that stuff. But it's difficult because it's like, those guys are kind of interesting, but like, at the end of the day, like similarly to what you're saying, Michael, about like the act of measuring disturbs the system, and like that's the whole thing. And it's like, absolutely. But like, but what about these specifics? Like the fact that it's like complex vectors, not real vectors, or like it's d squared instead of d, or like this and this. Like, what about these like really technical things that like set quantum theory apart from like all the other theories that have that quality? Similarly, you read the phenomenologists and they're like talking about horizons and perceptions and relationships and trying to like rethink the subject object description. And that all sounds really cool. But then you're like, well, how do I get the Born rule from that? How do I get my complex vectors back from that? So there's still like this disconnect, It's like, how do we say something like intelligent, about the nature of the agent in a way that like respects our experience and the nature of our perceptions, but at the same time, like actually internalizes the mathematical lessons of quantum theory itself. And that remains like a really difficult problem, I would say.
But we have to make a distinction between physical reality and the math that we use that attempts to describe it. And
For sure.
And the Born rule to me is just he pulled it out of the nearest orifice that he could find. It's just to match what he was looking for. But to pick up on
what do you make of it when I say, oh, this is the Born rule?
Well,
like,
okay.
Isn't that interesting? Like, you can write it like that, it suddenly seems like it has a meaning, you know what I mean? As opposed to like, well, if I square the amplitudes and whatever.
But Matt,
I agree.
again,
It seems kind of put in, on the fly in a footnote. I think Born, puts it at some point.
But again, Matt, with respect, you're still talking math. You're not necessarily talking physical reality. Now, to pick up,
I'm saying this is something you can do, right? Like, you have this box and you send lots of stuff into it, and you can keep track of the conditional probabilities for like the outcomes of the box. And you send it into the box again, and then you get this little metric, and then you can confirm for yourself that like this number that you get, the transition probability, will be the same no matter what reference box you choose. And so like, that's why I called it a metric, because it really is reminiscent of kind of like a general relativity thing. Like, it's almost like, in general relativity, the idea that like in any infinitesimal point, there's always like an inertial reference frame. Like you can think about it that way. It's like here, it's like any informationally complete box will allow you to calculate the quantum transition probability. Like this is like this trans-subjective thing. Like if anything is trans-subjective or like kind of objective, if you want to use the word, in cubism, it is the Born rule itself. Like that's the thing that we all can agree about. It's kind of interesting to think about that in relate. And so I was trying to play that up a bit, like calling it a metric. But anyway.
But again, the Bohmians don't agree with that. Just to add that
I haven't had much
proviso.
time. I mean, Cubism is a young interpretation. I would say I would say it's really only come into its own the last 15 years. I mean, it had its predecessors and its long development, which Chris knows.
But to pick up on what Nathan brought up about perception of reality, of course, our reality is just based on our perception, based on what our senses can tell us. Nevertheless, there is, at least a lot of us believe, there is a subjective reality that transcends our senses.
Or an objective.
I'm sorry?
You said subjective, but I think you meant objective.
Yeah, I'm sorry. There's an objective reality, although not everybody agrees with that, including Fuchs. Fuchs, again, he says that he
I think it's
believes
also
in
a question
objective.
of, to quote John DeBroda at some point in an email, if I had any reason to believe that cubism implied solipsism, I would give up, because that's not a road I want to go down. In other words, cubists are all about the real world, but it's just a question of like, what is the real world? Like, what is the nature of it? Like, maybe reality has to be, like, it seems like if you're a Bohmian, it's got to be deterministic. It's got to be like materialistic in this very particular way. Of course, you're willing to have massive non-locality and like all this other stuff, but indeed it is deterministic. It is materialistic. And, if that's
Right.
like how you define reality, reality has to be that.
No, the guy's still going. He's a real genius. He's amazing. He's about 25.
I can hear you. I don't want to hear your compliments.
I'm gonna try to reel him in. He might be more useful to us than David. Michael.
There is
But he's still rolling. But I want to. How much time do you have? What I want to do is get his email.
Have you looked at Carlo Rovelli's new book, Helgoland or whatever? It's interesting for various reasons. Actually, in the Cubist circles, there's been some discussion recently about trying to distinguish what really separates Rovelli's relational quantum mechanics from Cubism. And there's some parts in Rovelli's book where he talks about Cubism and he, says some things that are not quite fair. But I like Rovelli personally, and I like the book. I bring it up because the final chapters are kind of interesting in the way that he relates quantum theory to some other stuff.
What's the name of the book, by the way, just to be clear?
Helgoland, which is the name of the island where the young
Heisenberg did his matrix.
Yeah, he had his hay fever, and apparently there's
that's a brand new book then, huh?
Yeah, right hot off the press.
Oh, okay, thanks.
Matt, wouldn't you say Rovelli is all over the place? And he's a showman. He's like all over the place.
It's funny. You're not the first person to say that. As someone who has a writing background, I like Rovelli because he is a bit of a showman. I mean, he's a good writer, and I think he does, a service to physics. He's unapologetic that his book is, kind of like.
There's a different perception of him. He happens to be a scientist who understands marketing. You call that a showman, which is somewhat derogatory, but I think there's a practical point to it, right? Why not? If you're going to do all that hard work, why not get your word out, right? Instead of being like some of these great geniuses who hide in the cave, he's quite the opposite.
No, I agree
Substance
with that.
behind it. There's substance behind it. That's what I mean.
I agree with that. I didn't mean showman and, as a
Derogatory way. I just want to clarify that.
But the point is, his theories are all over the place. That's more
Okay.
importantly.
Sure.
Well, I mean, yeah, loop quantum gravity, endless pages, endless ink can be spilled about
Right.
that. But what I brought it up though, because there's a really, an interesting chapter where he actually talks about Lenin and what's his name, Bogdanov?
John Lennon or
Vladimir.
Lenin?
Vladimir.
Lenin was reading a book on Marx. Which Lenin, which Marx? Marty would know the answer.
Bogdanov. Yeah, Bogdanov. Yeah. Sorry. Okay, so apparently I didn't know anything about Bogdanov. Really interesting guy. He was kind of a polymath, politician, writer, philosopher, a doctor, all this stuff. He was sort of influenced by Ernst Mach, as many were in the late 19th, early 20th century. And he was part of the Bolsheviks. And he got in trouble with Lenin, who, like, in the early, 1900 whatevers, wrote a book, against Bogdanov. And I just found this whole episode, as Rovelli describes it, very interesting because even before quantum mechanics, like, it captures this thing. So Mach is about, he's kind of one of the progenitors of, like, positivism and, in some sense, relativity, trying to be as, like, unprejudiced as possible about, subject and object and sticking to what's, like, observable and so forth. And Lenin is like, what is this bourgeois subjectivist bullshit? Everyone knows that a good Marxist dialectical materialist bites the bullet and believes in a materialistic, deterministic world of particles moving around in space and time, and to do anything else is fucking heresy. Okay, this is Lenin. This is what Lenin says in this book. Okay, again,
That's right.
And it's like, to me, it's like it's not at that point, about science. It's about politics,
Science is very political too.
Yeah, of course.
In fact, the people who are still married to Copenhagen theory are more political than they are open-minded, I would think.
Well,
Quick question for you, Matthew, something practical before I forget and we sign off. How does one reach you? I wanted to send you something about doing some diagrams for.
Oh, yeah, sure.
What's your, can you put your, like, how to reach you in the chat or something?
Yeah, definitely.
I didn't see anything on LinkedIn. You might want to put it there as well.
Oh, yeah, good point. heyredhat@gmail.com.
Oh, got it. Okay.
Yeah, I'd love to see your diagrams. I mean, I think that would really help.
Great. Thank you.
Yeah, and coming up, either next weekend or some weekend, maybe 2 weeks, I want to kind of like do a sequel to this where, the relationship to the usual formalism is, like, elaborated. So we could, like, talk about, like, well, how do you get, complex, the probability amplitudes and the complex vectors? How do you build them up into these generalized measurements and eventually recover and sort of prove that everything that I said today, is equivalent to the usual formalism. In some ways that territory I went over in some of our, like, recent meetings, about this one, number 43 on cubism. And, 47, 48.
Actually, what are we looking at here? It's hard to see. It's kind of small.
Oh, I'm sorry. The last couple months, we've had several meetings about cubism. So like,
Where are all these listed?
oh yeah, heyredhat.github.io.
Oh, got it. Your previous site. Right. Thank you. Thank you.
So, our initial one about cubism was this first one here. And then, sort of get into different sort of aspects of it here in these other two, 47 and 48. But yeah, I want to do, basically coming up, we'll have Welcome to the Lab Part 2, and it'll be about, where the complex numbers come in, interference, which is really what they're useful for, and how to recover all this cubism stuff from that. But yeah, I think the overall message is like some interpretations of quantum mechanics, I would say, pretend to have all the answers. Cubism, bless their hearts, are more likely to confess ignorance and are sort of, basically their mode of investigation is to try to rewrite and reformulate quantum mechanics in lots of different ways and try to sort of divine out, where that's leading and try to stay as unprejudiced as possible. But of course, I do love a good Bohmian theory. As I say, Michael, Rovelli wrote a paper about Bohmian mechanics, and he was, it was funny. He was like, I didn't think it could work, but it really does. It really does work.
Do you know what the difference is really?
What? Oh, here it is.
It has to do with where
Bohmian mechanics.
it has to do with where you're assuming the probability is.
Mhm.
And with Bohmian in Copenhagen, the probability is assumed in the measurement. In
Yeah.
Bohmian mechanics, the probability is not really a probability. It's a statistical distribution of the initial conditions. We don't know what the initial conditions are.
Yeah.
If
totally.
if we did, then we would have a completely deterministic theory. So it's where do you place the probability? It makes more sense to believe that there's a statistical distribution of initial conditions, which makes the rest of it deterministic. It's just that we don't know how to measure those initial conditions.
Yeah, but of course, there's like, in Bohmian mechanics, like an essential limitation. Like it's not even like, it's not that you don't happen to know this probability distribution. It's like you couldn't even know it. And so,
well, you couldn't know it because again, it's the measurement problem. If you measured it, then you would be disturbing the initial condition. You'd be changing it.
Okay, well, for sure. But even in Bohmian mechanics, like if you did know it from the very beginning, and you would be able to predict the results of all the measurements, no matter how disturbing they are, But you could invoke Occam's razor and be like, well, no one could ever know this thing then.
But again, as I said in the beginning, all of these theories are non-relativistic. Once you go to quantum field theory does away with particles being point objects. There ain't no such thing as a point object, just as there's no such thing as a point. It's a geometric construction.
Well, this brings up a good point, which is like, one of the interesting things about Bohmian mechanics is it's like you do need this like representation in space and time.
But Bohmian mechanics also, Bohmian mechanics is just like Copenhagen in that it assumes point particles. And point particles are not real. They're an abstraction.
I think that's like a specific case. Like, for example, everything we talked about today was just the case of finite dimensional quantum mechanics. So, if you really believe that like particles are described by, wave functions that like extend, infinitely out in all directions or whatever.
Well, that's what QFT says.
Yeah. Then it's like
field disturbance.
Not enough. this is not enough. But I mean, it's interesting that Bohmian mechanics requires you to pay attention to the position. I mean, no matter what you care about, spin, other properties, it bottoms out in position. So it's like you can't really do quantum mechanics unless it's in space or maybe momentum space. I mean, we talked about that a couple months ago. Like you could imagine it kind of the point particles being in different kinds of spaces. But like, I mean, here we've just been talking about, I mean, in a way, no positions at all. I mean, we're just considering finite dimensional systems wherever, whenever, like, you know what I mean?
Yeah,
And
but as soon
it's
as
an interesting question, like how to think about,
yeah,
you know, like there's some people who believe that the infinities that are normally invoked, even in standard quantum theory and in quantum field theory, are mathematical devices that like there's a maximum amount of information you can have in a volume of space. The Hilbert space must be finite dimensional. Therefore, in some sense, finite dimensions is all you need. The fact that you can't implement the canonical commutation relations between position, momentum, be damned, you know? Finite dimensions is all there is. And I think to some extent, cubists do take that attitude that like all of the essential issues in quantum theory are to be seen in the finite dimensional case.
but a finite,
Maybe that's not okay. I mean, I don't know. I'm not sure how
a
I feel.
finite dimensional Hilbert space implies point particles. In QFT, you have an infinite dimensional Hilbert space if you want to look at it that way.
I mean, you have that in normal standard quantum mechanics. I mean, you just, and every time you use like a wave function, it's like in one dimension. It's just like a assignment of probability amplitudes.
Yeah, but a wave function is not, a wave function is not physical. A wave function is not physical. In QFT,
You don't need to go to, I mean, I'm saying it's like, that's infinite dimensional. I mean.
but I'm saying in the physical world, a point particle is spread out over space and time. It may be confined within a certain region, but it's spread out so that its Fourier analysis is a continuous Fourier analysis. It's not discrete,
For sure.
which means it's infinite dimensional. It has an infinite number of harmonic oscillators. It's not a point.
Yeah.
That's what QFT is telling you. And it solves the Heisenberg uncertainty principle and probabilities and all this other stuff that non-relativistic theories cannot give you.
Yeah. So like there remains some really deep questions about, you know, the nature of the infinite and its role in the physical world. And it's, you know, for millennia, I mean, truly, that has been you know, an issue people have batted around. And yeah, I mean, I think in both the normal, you know, the textbook, like single particle quantum mechanics and in quantum field theory, yeah, that is the issue that comes up. I don't know what the cubist answer to that is. I mean, probably, you know, that in some ways the infinities are math.
But has cubism been migrated in any way to a field theory? Or it's still we're still in the non-relativistic realm?
Yeah, you know, not that I know of. I mean, I've been talking to some of these guys and reading some papers. They have thoughts about it, but yeah, nothing really concrete.
See, I don't see why all this attention on these non-relativistic theories when we have the most accurate theory that's ever been devised. Quantum field theory, and more specifically, quantum electrodynamics.
I mean, I think the purpose was to kind of like, you know, distill quantum theory down to its essence, you know, which I tried to do here. And it's like, I mean, if you're dealing with infinite dimensions, like a lot of what I said doesn't make sense, right? Okay, like dimension D, and then you have these beautiful reference measurements, seeks that have D squared outcomes. And it's like, what if your Hilbert space is infinite dimensions? You know, I mean, you can have Pavms, right? You can do it like a coherent state decomposition. And in fact, like in quantum field theory, like one does this where, you know, you can basically treat classical, you know, configurations of like a field as being coherent states and like decompose like the quantum field in terms of those coherent states, which, like, these reference measurements we've been considering are overcomplete, they're unreliable, et cetera. Like in the, the classic examples with the harmonic oscillator, where you can take the vacuum state and act on it with like all the infinity of displacement operators, and then, basically create like a wave function that assigns an amplitude to the overlap, where like you get the overlap between, your given state and all of the displaced coherent states, or like the displaced vacuum states, which are coherent states. So, many of these ideas come into play, and generally go under the name coherent state quantization and stuff. But yeah, that's a continuous representation. So you don't have this sort of like very beautiful like d-squared outcomes for an informationally complete measurement. And certainly, if you think about the practical issue of quantum computers, they're built out of qubits mostly, and it's like finite dimensional. And so if we, you know what I mean? Like there is something core, essential about the finite dimensional case. And it's like a deep issue, like whether that licenses us to go making grand statements about all quantum systems and so forth.
But again, quantum computers, like any computer, are just process a simulation of reality. So don't take the outcome of a quantum computer calculation as reality necessarily. It's a simulation at what we believe reality to be.
They really are qubits made out of spins or whatever, junctions or something. You just might be using those qubits to simulate something.
They're qubits, but a qubit is a mathematical construction. And when you put it on a quantum computer, it's a simulation of what you believe reality to be. It's not necessarily reality. But again, this thing with infinite dimensions, Hilbert space, again, is not physical space. What Hilbert space is really a Fourier decomposition of the function.
Well, again, it's like, the relationship between a position wave function and a momentum wave function is given by the Fourier transform. But you can like do quantum mechanics on like lots of different kinds of spaces. Like, you know what I mean? Like, and there might be some kind of idea of the Fourier transform. But it's like you consider spin degrees of freedom or other degrees of freedom. The meaning of like a Fourier transform, is...
Well, spin is a whole different animal. Spin is discrete.
Yeah.
Spin is discrete. But Hilbert space per se, discrete Hilbert space is really meaningless because it's implying point particles. And again, like I said, quantum field theory.
I don't understand that connection.
Quantum field theory is basically telling you that the Hilbert space is infinite, it's continuous.
Realize like you can
Fourier decomposition.
You realize you can take a product of a finite dimensional Hilbert space and an infinite dimensional Hilbert space. Like you can have a particle on an infinite line, and at each point there's like a spin state. Like it can be both.
Yeah.
And like in the case of spin, it's X, Y, and Z that are related by the Fourier transform. Like instead of there being like a complementarity between position momentum, which is like a two-way duality, instead there's a three-way where like, X, Y, and Z are each, mutually complementary with each other, which is interesting.
But it's discrete, it's not continuous, whereas quantum field theory, as it describes particles, is about a continuous Fourier transform.
That's the way it's been conceived, and we'll see if that ends up being the final word on it. I don't know.
Well, it's not the final word, that's for sure. I don't think that we're capable of getting the final word because, again, our brains are limited.
Amen. Well, I should probably go relatively soon unless there's other burning
Okay.
questions. This has been great. Thanks as always for an
Yeah.
awesome discussion after my quite long, lecture. Thank you for sticking with it. It's been great.
So when is the next one next week, or you haven't decided?
Either this week or next week.
You know, what I would suggest, if you want greater attendance, I know something like 30 people signed up, but only 10 of us showed up.
Yeah.
But what I would do, I don't think that the members of the New York Quantum Theory group were aware of this. So what you should do, use my email list. If you get an email from me, you're on my email list. Use that list to
Yeah.
notify the. You know who I think should be? I keep repeating this, but I think Barry McFarland would really be interested.
Yeah,
in this.
Barry and I feel like we've just been kind of ships in the night, like not overlapping as much,
He's a mathematician. He's
Yeah.
into all this, heavy math stuff, and you should, try to get him to attend. But he's on, my email list. So send, a notification using my email list to the New York Theory group, and you'll get. I'm sure a lot of them will attend.
What's
Yeah.
this group about it? That's new to me. What's this list of yours?
Well, this group is the Brooklyn
Right.
quantum group. There's a New York quantum theory group
Okay.
that we meet on Sundays. In
Oh,
fact,
okay. You'll forgive me. I'm out in the West Coast. I never figured out all the various suburbs of Brooklyn, New Jersey, and how they're all connected. But anyway, okay.
Well, if you go to Meetup,
Yeah, here.
No, I know. I was being sarcastic. So in other words, to get on your list, all I got to do is join that meetup, New York.
Yeah.
Theoretical.
okay, well, Matt just posted it here, and we have a meetup. We have a meetup.
Okay,
tomorrow.
thanks.
We have a meetup tomorrow where we're going to discuss Paul Steinhardt's ridiculous theory of his cosmic
Bouncing.
his cosmic cyclic universe.
And
Which
this is
I
what you
think-
meant. In other words, this is what you meant by your mailing list.
No, but I have a mailing list that is mostly the members of this group, and Matt is on the list. I think Marty is on the list.
Can I give you my email in the chat and add me to it?
Yeah, okay, I could do that. But a lot of it is like a lot of contentious, arguments.
I don't
about
always
quantum
respond.
theory.
I
I don't
don't
know
always
if you
like
want
paying attention.
I don't know if you want to read all my emails, because a lot of it is nasty, contentious stuff where I disagree with the standard approach. I'm a Bohmian. I don't agree with the Copenhagen theory at all.
Well, okay, I'll give it a try. I guess I can always unsubscribe, right?
So it's Nathan at quantumcurious.org. That's easy to remember. I'll add you to the list.
QuantumCurious.org.
I just
Oh, yeah,
noticed
check
it.
that out. It's a site for, it's a very solid site. It's curated for beginners. It's got a lot of solid material there that I've been, just very quickly, in the last 3 years, I'm self-studying. I retired and I've always had a fascination with math and physics. So, you enter the winter of your life, you realize, hey, there's only so many months left. You might as well make advantage of it. And so I went on a binge of math and physics, and that site represents my learning experience.
Oh, but Nathan,
For beginners. Sorry?
Nathan, if you're interested in the New York meetup group, yeah, we're meeting tomorrow at 4:00 Eastern. So that where are you? On West Coast?
I'll at least join it.
So that'll be 1:00 your time. 1
Right.
p.m. your
I'm going to
time.
sign off. I'll follow up with you in an email, Matthew.
Well, you have Matthew posted the.
Right, that's what I said. I said I'll follow up with them. I'm going to sign off now, but you'll hear
Okay.
back from me soon about those diagrams. Thanks for the talk.
Yeah, thanks for
Glad we
coming.
met.
Yeah, thank
Okay,
you all.
thanks
Thanks.
again.
You too.
Thanks, everybody.
So long.
Bye-bye.
Adios.
Yep.